Should we start?
Yes, we are good to go.
Okay. Who is the first speaker?
I think it's Zijian Hu.
Zijian is here.
Sorry, I'm the first. So I thought I was the third one.
Yeah,
Okay.
Can I share your screen, please?
Okay, but I can start it.
Yeah.
Okay.
Okay.
So can everyone see my screen?
Okay.
Okay. Thank you. So good evening, everyone. My name is Zijian Hu, and I'm a PhD student at the Hong Kong Polytechnic University. And today I will share our work on towards very large-scale traffic simulators for multi-agent reinforcement learning test bed. So traffic simulation is are widely used for making policies for management or control in transportation scenarios. So for example, we can use simulations to figure out how to minimize the travel costs in a region by controlling the inflow and outflow rate, or how to control the intersections for signals to minimize waiting time, or how to control a ramp to avoiding potential traffic accidents and congestions. So actually, these three tasks are finished by three different simulators named Sumo, CityFlow, and Visa. And based on the scope and the resolutions, so current traffic simulator can be mainly categorized into microscopic, mesoscopic, and macroscopic. So currently, most simulators for reinforcement learning based are microscopic based. So actually, they're controlling the accelerations and the directions of the vehicles, but they are not suitable for the large scale simulations due to the model complexity. And if you can see that most total works are only tested on the local networks. And for the mesoscopic simulations, the flow of vehicles is controlled. So the vehicle movement is simplified, which makes it possible for large-scale simulations. But the gridlock effect will be hindered by will hinder the accuracy of the simulations. So actually, the gridlock effect is a special case. Is a special case of the traffic congestions. So in these animations, each dot represents vehicles, and different color means they have different destinations. So actually, vehicles are eventually hindered by the downstream vehicles, and they cannot exceed the roundabout unless we throw away some vehicles. So actually, in other simulators like Sumo, it is prone to happen, especially at complex intersections. So generally, if we generally the gridlock effect is common to happen during the large-scale simulations. And for the macroscopic models, they are widely used for the urban planning, but since it abstracts too much information, so they are not suitable for the traffic control and management. So in this project, we aim to large-scale simulations without gridlocking. So in this project, we propose macro level traffic simulators for the citywide control and management. And we mix different traffic models into a single simulation to avoid the gridlock and to enhance the simulation efficiency. And finally, we evaluate the simulation result on a city-scale network within 24 hours. So this is the structure of our simulators. So for the input, generally, we have the original destination demand data and the network data. And in the first step, in the simulations, we calculate the path and the assignment and assign a path for each vehicles. And in the second step, during the simulations, we prepare three different traffic models, BASA models, CTM cell transmission models, and the link transmission models. And since they can individually run in different regions simultaneously, we also design several connectors and node models for the communication of different models. And finally, after the simulations, and we can convert the output data into the two videos. The first video depicts the vehicle trajectories, and the second video depicts the link density variations in a day. So before the simulations, we prepared two assignment methods. The first one is all or nothing assignment. So basically, it's just calculate the shortest path to all vehicles and assign all vehicles to the shortest path. And the second method is called incremental assignment. So in this method, the key idea is to split the vehicle into T pieces, and for each pieces, and we can calculate the shortest path based on all or nothing assignment and assign them to the path. And then for another pieces, we recalculate the shortest path according to the total travel time and assign again until all the vehicles has been assigned. And for the method macro simulations, we prepare 3 different models. The first one is called the first 2 are cell transformation model and the link transformation models. So for the cell transformation model, so basically we just separating the links into n segment. So for each segment, we call it a cell. So the vehicles in the former cells can evolve into the latter cells. So during the simulations, actually we're just maintaining the vehicle number in different cells. So it is called the cell transformations. So actually it is a well-known traffic models in the transportation research. And another model is called the link transformation model. So actually we're just maintaining the upstream and the downstream vehicle accumulations during the simulations. So actually these 2 models are highly correlated with the link attribute. So in the simulations, we need to go through all link, which is not efficient. And if the link is improper set, and the gridlock effect may appear. And another model is called the BASA model, which is a little bit different. So in this models, so for example, if so in this model, so we have 2. So in this models, we assume that the average traffic speed is correlated with the average traffic density. So for example, we have 2 vehicles in a region represented as red and blue. So although they have different OD and different route, but at the same time, their speed will be the same. So you can see that in these models, so that it do not correlate with the link attribute. So which means that we don't need to go through all links in the simulations, and the gridlock effect may be avoided. So in a nutshell, this is a comparison between the CTM, LTM, and the BASA models. So for the CTM and the LTM models, the vehicles in the vehicle are manipulated by the link density or link flow. And in the BASA model, the vehicles are driven by the regional densities. So according to the different characteristics of different models, so CTM and LTM models may be more suitable for the highway modeling, while the BASA model may be more appropriate for the residential or business areas. So here we also present an experiment to evaluate the simulation result for our simulators. So we adopt sumo scenarios for Turin, city of Italy. So in these scenarios, we have about 27,000 nodes and about 80,000 links. And the total demand is about 2.2 million vehicles in 24 hours. So initially, we use community detection algorithms to partition the whole network into 84 different regions. And initially, we compare the simulation result with CTM, LTM, and the BASA model. So this 4 picture depicts vehicle accumulations in 4 regions. So you can see that in the CTM model and the LTM model, the vehicles there is an explosion of vehicle accumulations, which is a sign of the gridlock. And if we track the congestion link in the map, we can see that the congestion links forms a circle. So means that it gridlocks. So, but the BASA models do not show any sign of the gridlock effect in the networks. And we can also compare the BASA model with the hybrid model, CTM model, and the SUMOs. So the hybrid model means that in the 84 regions, 82 regions are run with the BASA model, and 2 regions are run with the CTM models. And note that for the SUMO, we just use the mesoscopic models, not the microscopic ones. So you can see that for the normal demand, the BASA model only takes about 46 seconds to finish the whole simulations. And the hybrid models only take about 10 minutes. But the SUMO takes over 4 hours to finish the whole simulations. And if we double the demand, the Basa model still takes about 2 minutes. And we didn't test the case for CDM and Sumo since they already have difficulties in single demand. But when the demand is small, you can see that the Sumo can finish the simulation in a short time, and there is no sign of the gridlock for the vehicle accumulations. And we also prepare some visualization animations for the result. The left-hand side animation shows the vehicle trajectory of each vehicles. So the longer the tail is, the faster the vehicle drives in the map. And the right-hand side videos shows the link density variation in a day. And I think this is close to the dusk. And when it's come to the morning peak, the vehicle increase a lot. And this is about the noon. And this comes to the evening peak. And finally, it comes to the dawn. And combined with multi-agent reinforcement learning, these simulators can serve for several potential applications. For example, like the vehicle rerouting problem or the jointly controlled foot ramp and perimeters. So here we show a small example of the latter case. So for example, in this case, the agent can be defined as the ramp or the perimeter of the region. So for example, in this toy networks, we have 2 residential areas and one CBD areas. So these 3 areas can be modeled with the Basa models. We also have a highway and a ramp. So these 2 links can be modeled with the CTM or LTM. So for the observation of each agent, it could be the inflow and outflow and the vehicle accumulations. And for the action of the ramp, it could be the on-ramp rate. And for the action of the regions, it could be the inflow and the outflow rate. So in this task, the objective is to minimize the total travel time. So the reward could be the negative number of the running vehicles on the road. So also convert the simulators into a gym fashion API for users to use. So you can see that for the observation for each agent is 3-dimension vectors, the inflow, accumulation, and outflow. And the action just the control rate for each agent. And this environment can be directly trained with the algorithm in the RL4ITS package. So here we show example of the algorithm of the DDPG. And since it is still an ongoing project, and we are still testing the benchmark for the environment. And once we finish, we will open source our code for everyone to use. And that is all for my presentation. And thank you very much.
Thank you.
Thank you.
Any questions? Could we take one short question? One small question?
No.
If no questions, we thank the speaker again. Who else the second speaker?
How do I know?
I'm the presenter for the next paper. Shall I begin now?
Who are the second speaker? Somebody has a question.
Chengguang, I think you are good to go. You can share your screen.
Okay.
Yeah.
No.
So does my screen work well? Okay. So good evening, everyone. I'm Chengguang Zhao. I'm currently a master student at Beihang University. Today, I'm very lucky to give the presentation about PRG Light, a novel traffic light control framework with pressure-based reinforcement learning and graph neural network. I'm going to unfold the presentation from the following 5 aspects. First is the research background. Traffic congestion has become an urgent problem, especially in the urban network. So traffic light control has been considered as a promising research area. Nevertheless, existing reinforcement learning algorithms may have ineffective utilization of traffic information. For example, how to we make full use of the large volume of real-time traffic data and how to reflect the effectiveness of the algorithm. Besides this, another important thing about reinforcement learning is that it's based only on current traffic state and there is no future traffic information. So to deal with these 2 problems in this work, our 2 main contributions are that first, we design a novel PRCOL and set it as the reward for reinforcement learning. And second, we integrate a GNN module to predict future traffic, and then we jointly control the light phase and the duration. Here is some related work. Wei and Chen, they have set max pressure to reinforcement learning. In our work, we further improve this index and propose a novel pressure algorithm. Yu has proposed a graph convolution for traffic prediction. And in this work, we combine traffic prediction and the reinforcement learning to control the traffic light. So we study the traffic light control in a multi-intersection road network. In an intersection, there are 4 directions: north, south, west, and east. And for each direction, there are further 3 lanes, that is turning left, going straight, and turning right. So we have 4 times 3, that's 12 incoming lanes. A vehicle will approach the intersection from an incoming lane and then leave from an outgoing lane. We call such a route traffic movement, and so there are totally 12 traffic movements. We combine 2 of them as a pair and call it a light phase. So there are 4 light phase here. We suppose that the turning right is allowed anytime. And in our work, for the traffic light phase control, we use reinforcement learning approach. There are actually 3 key elements to design a reinforcement learning agent: state, action, and reward. For the state, we denote it as a 12-dimension vector, which represents the number of vehicles on the 12 incoming lanes. And for the action, we choose 1 light phase from the 4 light phases. For the reward, we propose a novel PRCOL, that is pressure with remaining capacity of the outgoing lane. It's defined as N in, which is the number of vehicles in the incoming lane, times 1 minus N out over N max. N out is the number of vehicles on the outgoing lane, and N max is the capacity. So for this example, there are 2 vehicles on the incoming lane and 1 on the outgoing lane. And the capacity of the outgoing lane is 3, so we can get PRCOL as 2 times 1 minus 1/3, that is 4 over 3. And we set the reward as the minus PRCOL over the sum over the 12 traffic movements. And for the traffic light duration control, first we adopt a graph neural network to predict the future traffic attributes as t. With this predicted result, we suppose that Fn is the time for n vehicles to pass the intersection. We first get a required duration, that is t required by current state. It is equal to Fn pass. Here n pass means how many vehicles can pass in intersection now. It's defined as the minimum between n in and n max minus n out. And then we define an expected light duration, that is T expect, and is defined as FNP. Here, NP is the predicted traffic volume. Finally, we can get the light duration as the minimum between of T expected and T required. So here is a framework of the algorithm. As can be seen, current traffic state ST is used to decide the light phase. The light phase together with the current and the future traffic state are used to decide the light duration. Here is the algorithm code. In each loop, we have 3 main steps, that is predict the traffic state and choose light phase and decide light duration. For the experiments part, we first run experiments on one synthetic data set. We compared with 3 baselines. It can be seen that the proposed PRG light achieved the lowest travel time and the highest throughput among compared to the 3 baselines. We also show the results for 2 lines for PRG light, which is PR light and G light. For PR light, we only keep the PRCLR module, and for G light, we only keep the G light module. These 2 variants yield longer travel time and lower throughput, which demonstrates that both of the 2 modules are effective. We also test on 3 real-world data sets, that is Hangzhou, Jinan, and New York. Compared to the state-of-the-art algorithms, CoLight or Marca, our PRG light can achieve lower traffic travel time. We also report the standard error of the experiments in the last line. In this table, we tested the role of prediction and the dynamic duration. We show 4 algorithms as shown in the first column, that is fixed, dynamic, HA, and the PRG light. For fixed, the duration is set as a constant, and for dynamic, the duration is dynamic, but it's based only on the current condition, and there's no future traffic condition. For HA, we consider both current and future condition, but we use history averaging to predict. And for PRG light, we use neural network to predict the future traffic information. So among these 4 algorithms, the PRG light achieved the lowest travel time, which shows that the neural network and the dynamic duration both works. So in this figure, we give the predicted and real traffic volume. The right line is the real traffic volume, and the blue line is the predicted traffic volume. It can be seen that the prediction and the real curves show approximate trend, with the real curve having more vibrations. And finally, we also analyze the number of vehicles and the choice of green light. Take Hangzhou as an example. It can be seen that phase 0, the red line, has more number of vehicles compared to the other 3 phases. And so in the right figure, the phase 0 is chosen more frequently than the other 3. We take apart from the whole figure and get the lower figure. It also can be seen that for the phase 0, the red line, it is chosen more frequently than the other 3. So the phase with maximum number of vehicles will be chosen priorly. And that is the end of my presentation. Thanks for your listening. Okay, I see a question here. Since the agent's since the policy keeps changing regularly, how do you comment on no? I don't think so. The future state is not depend on the agent policies. Agent is decided based on the current, like you mentioned that the future depends on the policy. The agent policy, I understand, is to design the light phase based on current, as in this figure. Whether you mean this one? 王家伟。Does the prediction model depend on the control decision? Currently, no. We pre-train a network and use the result. Maybe that is a future direction. Okay.
I have a question regarding the previous paper, the simulator paper. I just want to make sure that I understand correctly. So the main difference between the proposed simulator and an existing simulation environment, for example, the flow simulator for traffic simulation, is it that the proposed simulation environment it's based on it's not based on individual vehicles, but it's like more on the higher level, like on the flow level, or
Yes. Yeah, I think that some most current simulators, yeah, they are based on the single vehicles, like the smarts from Huawei or the CityFlow, or I think the simulator for the previous speakers. Yeah, but the simulator for our in our research is not regarding the individual vehicle as a unit, but regarding the flow of vehicles as a unit. So actually, we're controlling the flow. There won't be any individual vehicles. Yeah.
I see. So in that case, are you able to support simulation of those dynamic or adaptive policies? Like since I saw that you in your setting you assume that you do the traffic assignment, right? But for reinforcement learning based policies, usually they are adaptive and dynamic policies. You make the decision at the junctions. So I'm wondering like whether that kind of thing is supported.
So you mean that maybe we can change the route during the simulations, or? Yeah.
Basically, the decision point is at the junction, at the node.
Yeah. Currently, we just fix the assignment. Yeah, for example, we use shortest path. We use all the shortest paths for all simulations. So yeah, currently we just control the junction for the inflow and outflow. But I think in the future we may change the route during the simulation. I think it may be better. Yeah.
Okay. Thanks.
Okay. Thank you.
Yeah.
Professor Young, you're here.
Hi, hello, hi. Just come here.
How are you? Long time no see. Are you in
Yeah.
office?
My coffee time. Just come to office.
Haven't seen you for a while.
Yeah, already long time.
Hi, Professor Yang.
Hey, hello.
You haven't leave Hong Kong for how long?
Almost 2 years. Every day just yeah, home, office, office, home. Very boring.
It's tough time. Very well. We still have 5 minutes. I think we're gonna start from like 7:55.
So my turn next one.
Yeah, you'll start from 7:55.
Oh, 7:55. Okay, maybe I can share my PPT first.
Yeah, you can share your screen first. I saw some advertisement regarding to the what's that school in Guangzhou?
Oh, our yeah, we are the 3 times bigger than Kenyatta Way.
3 times bigger?
Are you interested in coming here to be our? We are looking for vice president. We already have a president.
No.
So you may apply for our vice president.
I want to relax for a while. I don't want to do too much work. Too much work.
So I just help develop the intelligent transportation program. So basically now I have 2 jobs, very busy.
Are you going to get a double paid for doing that?
No.
That's why I can't.
They give me a little allowance, but the hourly rate of allowance very very
It's
low.
better than nothing, right?
Yes, not so much time. We prepare recording faculty member, prepare the syllabus, and too busy. So so you already in the US for some time, right?
Yes, I have been
back
for almost 1 year.
1 year. So when you come back to visit the mainland Hong Kong.
Yeah, maybe. Who knows? This depends on the COVID.
Yeah, the quarantine. So we still, we still need to go to about 3 weeks quarantine if we go to mainland. So
no, how long you have to do quarantine in Hong Kong? For instance, I fly.
You come back. Maybe now the relax a little bit. If you have a vaccination, maybe 2 weeks. Well, 1 week in hotel, 1 week home.
Okay.
So, but now our semester will start very soon. So just stay here, nowhere to go.
Is your semester start or not?
Pardon?
No. This semester you already started or not?
No. Yeah. Oh, my semester. All semester from next week. Next week.
Next week, is it will be in person or just still visual?
This time we just have a face-to-face classroom teaching because we require all staff, professors, students to get
You get a vaccine.
Otherwise, you are not allowed to come to campus. Yeah, already, already, we already had an online teaching for almost 2 years, right? Since Hong Kong social event unrest, students, protest, then COVID-19 almost 2 years. So we cannot continue just this way.
Yeah, it's quite interesting. Nowadays, all the universities in the United States face a major deficit because of this visual classes teaching. And I think that the university face a lot of pressure.
Actually, I enjoy online teaching.
No, I think in-person teaching is better in the sense of you can basically interact with the students. Online teaching, you have to read your slides, and I think it's better for giving seminars, in particularly if you.
Yeah, that's very convenient for seminar, for research meeting.
I like that, but I think that for teaching, maybe it's better to do it in person.
Okay.
If you have this semester, I have 5 invitations to give a seminar, more than 5, giving different places. How could I handle it?
Yeah.
But now if we just give visual kinds of presentation, that's much easier, right? You can give 5 of them in a day. And they also, you can record it and you can play it in different places. You can just record it once and use it in different places.
No, we are not allowed to recording. Repeat previous teaching. You have to do it, in person. Not allowed to just play recording.
Well, it's good to record your.
But for students, to learn. It's good.
Also,
revision.
Also, you can put it on a YouTube or other social media, and more people can learn from it. I think that's good things, because nowadays it's very popular. People just put the video of their teaching on YouTube or Bilibili, and that's many people are really watching them.
Yeah. Some common core courses available online. Hey, Hong Kong. Hey, we just ask a question. Last year I submitted the GRF proposal, but unfortunately it was unfunded. This year I wanted to resubmit again. I think the panel member didn't do a good job. The reference report are okay, but I got a supporting letter from you, right? So I wanted to use the letter again. May I just change the date to this year? Is this okay with you?
No, I used to work with, but I think I'm not working at DD anymore. But I think you can. But I think one thing you can do is to ask Tony to do it. But if you, I can give you a support from UNC. That would be no problem. But I think if you want to do connection with industry, I think you better ask Tony to do it.
Oh, so you completely left. Okay, DD.
Yeah.
So okay, maybe I can talk to Tony for Tony, yeah, okay.
Yeah, and just change your name into Tony's name. Right, that's it. That's it. Okay, let's start.
Oh, okay.
Let me introduce you first before we started, I think. And good morning or good night, everyone. It's my great pleasure to introduce our next keynote speaker, Professor Hai Yang. Professor Hai Yang is the current chair professor at the Hong Kong University of Science and Technology. He's internationally known as an active scholar in the field of transportation, with more than 260 papers published in the SCI index and journals, and SCI H index citation rate of 60. Most of his publications appeared in leading international journals such as the Transportation Research, Transportation Science and Operations Research. Professor Yang received a number of national and international awards, including Frank M. the Masters Transportation Engineer Award, American Society of Civil Engineering in 2020, National Nature Science Award bestowed by the State Council of the People's Republic of China in 2011. He was appointed as the Changjiang Chaired Professor of the Ministry of the Education of the PI China. Professor Yang served as the Editor-in-Chief of Transportation Research, Part B, Methodological from 2013 to 2018, and is now a distinguished editorial board member of this prestigious journal. Welcome, Professor Yang. It's your turn.
Okay, thank you. Thank you, Professor Bruce. Thank you for your introduction. It's my pleasure, to give this talk about mathematics, economics, and the AI in the social market. And this is slightly different from the title and the abstract I provided to Tony, because I have 1 hour. I wanted to give a more general talk, mainly about the research my group has done so far in this exciting area. So my presentation will cover the 3 parts. First, the introduction to the social market, and second, mathematical and economic modeling in the social market. And part 3 will cover data analytics and the AI in the social market. I may focus on part 1 and part 2. If I have more time, I will move to part 3. But I think everyone here is expert in AI, machine learning, except me. So I just focus on part 1, part 2. And first, the introduction to the social market, and everybody know, the sourcing online mobility platform provide a timely and convenient, the services to everyone, anywhere, anytime. So now we have accumulated a massive amount of mobility data, which provide opportunity to deal with some of the most exciting scientific questions, such as human mobility analysis, city planning, traffic control, and management. So the better question is to divide this space into small elements. So here I give we develop a general modern framework. The objective of the platform to operators is to how to balance demand and supply over time of space, and also maximize the revenue and user experience and so on. And the strategy or decision variable that the operator can use to achieve the objective include the pricing, driver rewarding, order dispatching, rider pooling, and so on. So we have 2 major components in the market: passenger demand and driver supply. If we look at the driver supply side, which depends on your decision, such as pricing, and rewarding and the wage rate, the wage. And first look at the passenger demand side. The passenger demand side, the passenger demand, of course, depends on the passenger attributes, socioeconomic status, and the pricing decision by the platform, and also service quality. And also the passenger waiting time affect the passenger demand, and also passenger demand depends on the availability of alternative travel mode. This driver supply side also depends on driver attributes and the behaviors, and also depend on the car utilization during the service time, and also depend on the other job opportunities. So we have the four major variable or component, endogenous variable in the market, and interact each other, interdependent. For example, passenger demand affect the driver idle time or car utilization rate, and the car utilization rate affect the driver income and also driver supply. Driver supply affect passenger waiting time. Passenger waiting time in turn affect the passenger demand, and the passenger demand affect the driver idle time and then supply. So they interact with each other, and they interact together to determine the market equilibrium, and therefore the passenger demand and the driver supply. Okay, so the problem is how to choose the best strategy while taking account the market equilibrium of passenger demand and driver supply and your operating strategy to achieve your objective. So under this framework, we have a number of research problems: demand and pricing, supply and incentive for drivers, and the platform operation strategy. Theories and stochastic process integer optimization, stochastic and dynamic programming, game theory, machine learning, and right. As summarized here, this is from our survey paper published 2 years ago. So, in the following part, I briefly describe some mathematical and economic modeling problem in the sourcing market. All right. And in general, we have the following problem, as I mentioned earlier: human mobility analysis, which is a traditional problem studied extensively by physicists. And the temporal and the spatial forecasting of passenger demand and driver supply, and the ETA for both pickup and ride trip, and passenger behavior analysis. For example, even after order confirmation and the car is already on the way to pick up, but some passenger may cancel the order because maybe suddenly an empty taxi arrived. And also passengers will need to wait with sunk waiting time, and the driver behavior such as driver's income, profitability, and working hours. In particular, the elasticity of driver working hours, with respect to wage rate, which are economic issue. And matching and order dispatching, emergent case including ride pooling, and also allocation of resources for driver and passenger to balance a spatial and temporal distribution of demand and supply. Dynamic or surge pricing during peak hour, and the driver's zone choice behavior and guidance, and the reposition for empty vehicles. You may wonder why some taxi drivers are willing to wait at the airport, say for up to 2 or 3 hours to get one ride. And also option of bundled services of solo and shared ride. Passenger may make such a choice of bundled option. Then the platform have to assign the passenger to either solo ride service or shared ride service. So many interesting questions. And also incentive mechanism design for on-demand ride pooling, how to encourage the passenger to enjoy to choose the ride share. And the platform competition and cooperation. Normally multiple platforms compete with each other. And also we also have the problem of passenger driver multi-homing problem. And also recently we have a platform integration. Okay. Integration. And also, you know, we can, you know, we have to take into account the effect of rider sourcing services on traffic congestion and public transportation usage. Then how government should introduce some effective, efficient regulation and policy to make the market efficient. Right. So now I move to talk about some specific problem. I don't go to the details, just briefly outline the problem. Anyway, if you're interested in the problem, you may find out the published papers. So the first one, optimizing the machine time interval, not machine, sorry. Machine time interval and machine radius. So we have two major decision variables. The first one is the machine time interval. Normally, you know, we have a machine time interval to accumulate passenger and drivers for batch matching. And here is the example. If we have a short, very short machine time interval, for example, just 2 seconds, maybe we just have a few drivers and passengers. So it's difficult to get a successful matching. But if we increase the machine time a little bit, then we can accumulate more passenger, more drivers, more vehicles, so we can make closer matching, and we have more pairs of successful matching. This is, and we can also reduce the pickup, and this is the advantages. But the disadvantage is that, you know, if you increase the machine time interval, then the waiting time of passenger and drivers will increase, okay, direct. So it's a trade-off. And if we look at the matching radius, okay, if we use a shorter matching radius, you know, the success matching rate will be very low. But if we increase the matching radius, say from 1 kilometer to 3 kilometers, of course, we have more successful pairs of matching. But this is the advantage. But the disadvantage, you know, the pickup time or distance will increase as well. And more importantly, okay, the two decision variables, matching time interval and matching radius, are interdependent. For example, if we increase the matching time and we already accumulated a sufficient number of drivers and passengers, so we can already do the closer matching. So the matching radius constraint may become irrelevant, okay, or inactive. Okay, and of course we can develop some dynamic optimization strategy, okay, to solve the optimization problem of matching time interval, matching radius sequentially, okay, to determine, okay, sequentially based on the you know, from time interval to time interval, based on the newly observed and predicted supply demand conditions, right? And here are some results, and we found that the dynamic optimization strategy performs much better than the fixed time interval, fixed matching radius. And we can also choose a number of combination of matching time interval and matching radius, so we can design a menu. So you know, you can simply choose one combination based on the current observed demand supply condition and the predicted arrival rate of passenger and drivers within the current interval. So this will make the problem simple. We can use machine learning to, you know, how to choose the best menu, the option for efficient operation. This will be covered in the final part of my presentation. The second one is multi-objective, multi-partite online rider matching. The paper we worked together with Professor Gu. The paper was just published in Part C just last week. So, you know, when do matching, we have to consider, you know, different categories of riders, the participants, including rider pooling rider, was saw non-rider pooling was saw riders. And okay, also some passenger choose the bundle option. So okay, so this is a real situation. And we also consider different types of available vehicles. Say we have a complete vacant vehicles. We could have a partially occupied vehicle. The vehicle already has one passenger who choose ride sharing. So you can include one more passenger if if he or she choose ride pooling, ride sharing. And the information we have included the origin destination of the rider, location, and the status of the vehicles. Okay, fully or partially occupied. The matching method. Okay. And with matching agent, we can come up with the output of matching outcome and the performance. So this is a standard bipartite matching. We have pair and therefore different rider revenue or value, and the pickup distance between pair of a car and passengers. Okay, so the problem of matching could be a single objective or multiple objective. For example, we can minimize the total pickup distance, or we could maximize the platform revenue. Okay, based on the rider value. But this is the standard bipartite matching. But for the problem I just mentioned, the problem becomes more complicated because on the passenger side, we have a bundle option rider, solo rider service, okay, non-pooling riders and rider pooling riders. And for vehicle, we have fully idle vehicle, partially occupied vehicle with one rider pooling riders and fully occupied vehicles. And for example, okay, and here we could have two different matching outcome highlighted by red color and blue color, and the outcome will be, of course, different. For example, with this outcome in blue color, then all vehicles are fully occupied. But with the red color matching, we could have we have outcome 2. In this case, we still have extra service capacity because this vehicle is partially occupied by a passenger who choose ride sharing. So in this case, if we wanted to serve more passenger, and we should choose this matching outcome, and because we can accommodate one more passenger in next time interval, okay, in following matching time intervals. And pricing and equilibrium in rider sourcing market with rider pooling services. If we consider rider pooling published, and indeed, most platforms provide rider pooling services. The problem is that how to determine the discounted fare for passenger who choose rider pooling. This is a key issue. Okay, and with rider pooling, when we consider pricing or matching, we needed to take into account some extra factors such as the passenger drivers detour time, for pickup and drop off of second passenger. And also, you assign a passenger, rider pooling passenger to an empty vehicle, but maybe, sometimes you cannot find a next passenger to join. To join the rider pooling passenger en route. So we face a poor matching probability problem. Okay, whether or not we can have a successful matching en route, and also, okay, so we need to consider that, and so the passenger demand, average pickup time, the matching probability, passenger detour time, all such variables interact with each other. Okay, So we need to take into account such interaction when we determine the pricing for ride pooling passengers. You know, this is important. Why? For example, okay, you know, you use big data, use historical data. If you predict, you know, the probability of a successful matching is very low, very low. And then the platform may offer the passenger a very high price, maybe no much difference from normal or solo rider sourcing services. Because the platform has such information, okay? And in this case, actually the platform doesn't encourage you, okay? Doesn't encourage you to choose ride sharing, okay? Because you have to make announcement of the price, the fare to the passenger, right? So that whether the passenger can make a decision whether or not to accept your offers. But okay, if you predict that, okay, the high probability of successful en-route matching, then of course you can offer a newer fare. Okay, make sure the passenger will accept your offer. And but the problem is that you know, if you offer a newer fare, then this will directly reduce your revenue per passenger. This is the disadvantage. The advantage is that, you know, the fare decrease for ride sharing passenger, okay, you know, will attract more passenger to choose ride sharing. And increase in ride sharing demand will increase the matching probability, and which in turn, okay, you know, increase your revenue. So we have you know, two opposite forces, okay, right? In your determination of the price. Okay, anyway, this is a very complicated and interesting issue. Okay, pricing with ride pooling. You know, we have to consider, you know, different forces in the market. Modeling on-demand ride pooling market in the presence of congestion. You know, there are a lot of debate, particularly in the US, whether or not ride sourcing services and even ride pooling or ride sharing services make traffic more congested. Okay, some positive opinion, negative opinion. But we found, you know, answer to such a question is, you know, depend on two major factors. Particularly depend on the level of passenger demand. We have a threshold level of passenger demand. Over this level of passenger demand, often, okay, ride sharing or ride pooling services can help reduction in traffic congestion, because when the level of passenger demand is high, and ride pooling services can reduce net vehicular demand and therefore reduce congestion. And at the same time, we can serve more passengers. Okay, but if the passenger demand is not very high, if you still introduce ride pooling services, then the extra detour time for pickup and drop off additional passenger will increase, and which may contribute, okay, significantly to traffic congestion, make traffic more congested. So we don't have you know, a standard answer. Okay, it's depend on the demand level as well as the matching time window, the waiting window, passenger waiting time window. Okay. As we indicated here, because the matching window, matching time interval should be within a certain range. Beyond this level, you know, the passenger wait time will be long, so we don't have a win-win situation. And when we choose okay, appropriate matching interval or waiting window with a certain level of passenger demand, so we can create a win-win situation to both ride sourcing passenger and the normal private car user or the background traffic. They can both reduce time. the win-win situation. Okay, how much time already? Oh. So next one, okay, topic 5 under the mathematical economic modeling, integrated surge pricing and rewarding scheme. Now, I just briefly highlight the problem, okay? We use simple examples. Say, during the peak hour, we have a high demand, okay? High demand, normally we have the passenger surge pricing, okay, to balance the demand and supply. But the problem is that you cannot just arbitrarily increase the price 2 times high, 3 times high, you know, which make the passenger unhappy, which may create some social concern or social issue. But the problem is that, okay, suppose, okay, normally the basic charge for ride is 50 Hong Kong dollar. And normally acceptable surge price is $20, which may normally go to the drivers. But the problem is that even you pay this $20 normal surge price, it's still difficult to get a ride, get the response, get a ride service, because the parking queue could be very long. So we can think about this way. Okay, suppose the platform operator, ask for $20 more additional top up from the passengers. Okay, and if the passenger is willing to top up more, say $20, then the platform can give priority dispatching, offer priority services. But in order to avoid the problem I just mentioned, you know, to give people impression the platform arbitrarily charge the passenger, then this $20 additional top up is still the money of the passenger. It is saved in the designated passenger platform saving account. But you cannot use this the money in your platform account for other purposes, for shopping, for other purposes. Only, okay, during the off-peak hour, you still come to use my service, okay? Then you can get back this $20, okay, to subsidize yourself. For example, okay, the normal ride price is 50. You can get a $20 back, okay, or could just a $10 back, okay? And then you get this means you use your own money to subsidize yourself. So in this way, you know, we can create a win-win-win situation. Okay, from the passenger perspective, the passenger didn't really pay more, but they enjoy priority service during the peak hour. From the platform perspective, they keep the passenger, okay, to continue to patronize their services. And so because during the off-peak hour anyway, we have more supply, and then we can attract the more demand, passenger demand, we can have more transaction and more commission charge. From the driver perspective, it is also a win situation, because during the off-peak hour, you serve more rides, you can increase your car utilization rate. All right, so we can create a win-win-win situations. This is this question. And the next one, research issue is the customers will need to wait with the cycle waiting time. Okay, in rider, when you wait for rider sourcing services with the cycle waiting time. And you normally, when you open the app, you may have such information, say how long, how many passengers are waiting ahead of you, what is the current estimated waiting time. Then once you see such information, you have to make a decision. You stay with the app to wait, or you just simply need exit, okay, exit. So you will face such decision problems. Normally the online platform provided an updated queuing length and the estimated waiting time of matching at the current time point. Okay, and at any time, a customer can choose to leave or stay. I just mentioned in the queue based on the real-time information provided by the platform. And the customer in the queue make a decision anytime on the basis of your sunk waiting time. And a newly estimated waiting time. Then we may face a dilemma as described here. Have such a basic question. Suppose this is clock time with a reference 0, okay? Now, suppose you open your app at this at this reference time, and the platform tell you the current estimated wait time is 20 minutes. Then you have to make a decision, wait or leave. If you leave, then it is out of the question. If you decide to wait here, this means your maximum willingness to wait is at least 20 minutes. But the problem is that, after you wait for 10 minutes, 10 minutes passed, then the platform tell you the current waiting time for you is 8 minutes. But this means what? This means the situation has improved. The traffic conditions, the waiting time, the situation has improved, because if we still have the initial condition, your waiting time should be 10 minutes, but now the waiting time just 8 minutes. Of course, if you're a rational passenger, your decision is simple, just continue to wait, okay? But the problem is that after you wait for 10 minutes, the platform updated the waiting time and tell you the current waiting time is 15 minutes. This means the situation becomes worse than before. Then you have to make a decision. You continue to wait or you simply exit, give up. All right? But if you need, and you may think about it, I already waited for 10 minutes. But anyway, you face such uncertainty, so you have to make a decision. All right? So this is a problem we are studying. We're looking at this problem. I think it's an interesting problem. This this one. And the next issue is demand and the resource allocation strategy with a bundled service option I just mentioned. Okay, we are still working on this problem. The platform provides different types of services, all right, such as ride pooling services and express services. And they also, some platforms such as Didi also offer bundled service option. This means in Chinese, this is 同时呼叫, simultaneous call. Okay, you make your choice. Both ride pooling, non-ride pooling services. And this way, you may reduce your waiting time because this service your service could become more flexible. All right. So the option of bundled services. So you choose a bundle of service, but this is different from the bundled product. Okay, in other economic market. In the ride sourcing market, you choose a bundle of services, ride pooling, non-ride pooling, but eventually you receive only one of the bundled services assigned by the platform at their respective prices. All right. So it is different from the bundled product in regular market, where the customer buy all bundled product at discounted prices. So the advantage of introducing this option of bundled service is to increase the to make the service, to make the system more flexible to match demand and supply for achieving certain objectives. Then the question that we are facing the allocation of demand and vehicles or resources, okay, with the bundled service option. Say we have two queue, okay. Passenger and a vehicle queue for non-ride pooling. But if a passenger chooses such a bundled option, then you have to assign the passenger to this queue or to this queue, all right? And on the other hand, you have to allocate vehicle already carry one passenger who choose ride pooling. So you assign the vehicle to this queue or to this queue. These are resource allocation problem. These are demand assignment problems, right? So, and of course you have to consider this problem real time. Next topic. Competition and third-party platform integration in ride-sourcing market. Okay, and this is the proposal I submitted last year to Hong Kong funding agency, but unfortunately we failed to get the fund. And but I think this is very interesting research topic. You see, our paper is already accepted, by Part B, and one more paper already already received the first round review report, very positive, and the revised version is still under review. Okay, this is interesting new problem. And if you look at this platform, okay, so the platform integration, a transportation service provider such as Baidu or Gaode, okay, in mainland, integrate the rider services offer more platforms in a single app. Then passenger can send a rider request through such a third-party integrator and receive services from any one of the platforms, whichever respond first, okay, will become available. For example, okay, here you can see, you have the different platforms such as 阳光出行、滴滴快车、手机邀车, okay, and services with different prices. And the different type of service, 快车、出租车、taxi, express, or okay, the service type. So the passenger will see such 4 many of services. You can choose all services, or you choose some of the services available in the platform. Okay, so this is called platform integration. So, in the market scenario with the platform integration, okay, this is different from the multi-homing of driver and passengers. First, okay, passenger can request a ride service from multiple platforms at the same time. To their respective platforms. But in market scenario with multi-human, passenger patronize different platform by switching app. Okay, this is called passenger multi-human. Drivers are simultaneously affiliated to more than one platform. They sometimes put multiple, mobile phone in their car, all right, to get a ride, from a different platform. This is called driver multi-human. But platform integration is different from, of course, different from platform merging. In the case of platform integration, individual platforms still have a freedom to determine the trip fare and the operating strategy, while sharing some information such as the location of either drivers to the integrators. They still make the independent decision. But in the case of merging platform, this means two or more platforms or firms are merged into a single one to gain competitive advantages. So different. So the benefit of platform integration in ride sourcing market. The margin friction between passenger and drivers in general exhibit increasing return to scale. This means marching is more efficient as more passengers and drivers are involved in one single platform to generate a bigger or thicker market. We can, in this case, we can reduce margin friction. We can have a closer margin. So the advantage of platform integration is, okay, for example, okay, to alleviate or reduce the cost of market fragmentation due to the demand splitting among multiple platform. And more importantly, we can still maintain market competition of multiple platforms by independently setting their prices. Therefore, we can prevent charging a high monopoly price. We can still maintain market competition, while we can reduce the market friction, reduce market fragmentation negative effect. So our major finding, I just summarize here. First, okay, the platform integration can increase total passenger demand and social welfare, but may not necessarily generate a greater total profit for all the platform. So it's beneficial to the passenger. Second, platform integration can boost the profit of small platforms, but when the overall supply is not very large, it may hurt the profit of larger platform when the supply is sufficiently large. So this means it's not always good to big platform in the presence of platform integration, or in the presence of a third-party integrator offered by, for example, Gaode and Baidu. So, so this means the larger transportation network company or rider sourcing platform are facing a dilemma in the presence not a long time ago, I think last year. And this user mentioned that Didi was planning to disconnect the Gaode map interface. And the rider sourcing industry will change again, actually changed again. because the bigger platform will face such a dilemma. This means if you join such a third-party integrator, you are actually helping the smaller platform, all right? And but you will lose some profit, as I mentioned. It may hurt your profit. But if you don't join the third-party integrator, then all the other smarter platform join the integrator. Now, as you can see, okay, Didi just launched their own platform integration. Like Shenzhen, Zhuhai from their app. Didi now integrated several small transportation network company in its own platform. And okay, so anyway, the big platform will face such a dilemma. Topic line and mathematical and economical modeling, part 2. I'm still in part 2. Government regulation or government regulation policy in rider sourcing market. The government, but we will have a different regulatory outcome in the, This is the result without the consideration of traffic congestion. If we take into account the traffic congestion, the result might be slightly different. We may have the following regulatory regime. Price cap regulation. Just last week, I see the mainland the government just introduced a new regulation policy. They impose a ceiling, a cap of the commission charge by the platform. Okay, I think just last week. So price cap regulation and the maximum fleet size control, or even minimum fleet size control, or minimum wage regulation for drivers, and the commission regulation I just mentioned. Okay, your commission charge should be subject to an upper limit. And the utilization rate regulation. This means make sure your car utilization rate should be at least, for example, 70%. And the demand regulation, this means you have to solve at least a certain minimum level of passenger demand. And then under different regulation policy, the platform may have different choices or strategy in response to such regulation. And we can look at the parity efficiency, such as regulation policy. Parity efficiency. This means the parity efficiency is with respect to multiple objectives, such as social welfare, platform profit. All right, I think everyone knows what is the parity efficiency. And we proved that among all the regulation policy given here, only the commission regulation, the commission charge regulations, and the demand regulation are parity efficient. Okay, this means under such regulations, and the platform will choose their operation strategy in response to such regulation, and the market outcome will be parity efficient. So, okay, to achieve parity efficiency in terms of social welfare and the platform profit, and also including passenger and the driver benefit, passenger utility, driver income. Okay, this is part 2. I still have, so we still, I think how much time I have for my presentation, so we should have some time for question, right? Okay.
Yes, I think you still have 10 minutes.
For 10 minutes. Okay.
Or 5 minutes. At least 6 minutes.
Okay, then okay. I just briefly mention the part 3, data analytics and the AI in the social market, because you know this part much better than I do. It had big data. With big data, we found a home-shift distribution of network data ratios. For each completed ride service, we have the pick up ride. Okay, pick up ride, and we have the ride trip. Okay, the car go to pick up passenger here, and then take the passenger to the destination and on the road. All right, we have 2 rides, but our focus is on this part, the ride part. I will talk about the data ratio. So for any complete ride, we can define the data ratio as the ratio of the actual road distance to the straight line distance, Euclidean distance, this ratio. We wanted to look at the distribution of this data ratio with big data, okay, at the city level. So we had some data, okay, for some city. And first, we looked at the distribution of trips by distance in Beijing. Okay, the pick-up trip and the ride trip. it's, if we compare the distribution between text and the writer sourcing services, express services, different trend of distribution. Say, by taxi, by writer sourcing, different. Very interesting finding. Just I don't have time to talk about the details of why they have a different distribution. Simply because the taxi driver and the writer sourcing service platform have a different behaviors. And we found that this distribution, this home distribution law of network data ratio. This is the data ratio, the average data ratio at the city level, the data ratio against the ride distance. This means when the ride distance is short, say within the city center, urban area, then the data ratio will be distributed over a wide range, from nearly 1 to nearly 5. This means 5. The actual distance may be 5 times longer than the actual distance. But as the ride distance become longer and longer, then the data ratio will approach a constant value. And this can be well characterized by these simple equations. Okay, the data ratio is equal to, linear relation, linear function of the inverse. Okay, reciprocal of the ride distance. Okay, very good fitting. And we also found that the parameter betas almost constant for all the cities investigated. Okay, so we have such a universal distribution law. The parameters almost constant, very small change, variation over city, from city to city. And you may wonder why we have such a distribution. This can be explained because within the city, due to be just close to 1. For example, you move a passenger from here to just downstream here, you don't really have much detour. But if the passenger go to the other side of a highway or expressway, freeway, then you have to make a big detour, to get the passenger destination. So detour ratio could be 5. And for example, if the passenger just go to downstream, okay, very straightforward. But if the passenger move from here to here, and you have to make a big detour, so the detour ratio will be very high. So that's why when the ride distance is short, so in the urban area, the detour ratio, has a wide distributions. Okay, but if the detour when the ride is very long, for example, from the airport to the urban area, you don't have, you maybe just have one or two arterial road or freeway to choose. So so you don't really have much detour. So the detour ratio will be approach a constant, and which is about 1.3. And we can actually this the interesting problem investigated by mathematicians over the years. They found some theoretical value of the detour ratio for some special network, like the grid speed network, the detour ratio 1.25, and I don't have time, okay, to talk about the details. And our big data finding confirmed their theoretical result, okay. And for example, okay, our empirical finding 1.3, right? I think 1.3, very close to the theoretical result, derived theoretically for some special network. And the detour ratio distribution has many applications, okay, such as the service facility location logistic distribution network, and the data-driven analysis on detour. Sorry. detailed distance, routing distance, and matching probability in ride sourcing market. And when we consider ride pooling, we have the passenger detailed distance and the driver detailed distance. And we found, from the Chicago data, Uber data, we found that the ratio, the relative detailed distance of a passenger, delta L bar is the average passenger distance. L bar is the average trip distance without ride pooling. This is the detailed distance with pooling. And this relative detail ratio on the ride pooling services can be described as a function of the level of demand. Fit very well. You can see we have such a distribution. This is the detail ratio, relative detail ratio of passenger, and the average driver's routing distance against the poor margin demand. LD is the average driver's route distance. L bar is the average trip distance without ride pooling. For solving solar ride. And we also found that this ratio can be determined by the as a function, of the passenger demand, right? They fit in very well. And also we found that the matching probability for ride pooling can be also described as a function of the poor margin demand. You see, this is partially from some empirical data, Manhattan, Haikou, Chengdu. I don't need to go through the summary, just highlight the question. And then some AI, some machine learning application, temporal and spatial forecasting of passenger demand and driver supply. This is work mainly done by my former PhD student, Dr. Ko Jintao. He just joined the University of Hong Kong as an assistant professor. And learn to delay with the reinforcement learning approach together with the optimization of the matching time interval and the matching radius. Because at the end of each matching, some passengers, some drivers will be carried over, will be left, will be end up unmatched and carried over to the next time period. So the waiting time are recorded. So how long we should keep a passenger or vehicle waiting for better matching, for the overall better matching. This this the problem. The paper already become available in IJCAI transaction on knowledge and data engineering. How to dynamically adjust the matching time interval, matching radius, and also how to keep appropriate delay of passing environment using MDP. MDP. Yeah, you are expert in this area, so I don't need to go through the details. We use MDP, machine learning, to deal with this problem. And also learning how to coordinate the ride sourcing and the public transportation services to solve the first mile, last mile problem. In the city level, at the city level, we have a public transport, subway, buses, and we could have a ride sourcing car to provide access service to the mass transit railway to solve the last mile. And of course, you have to give incentive, to provide such coordinated complementary services to reduce the road congestion. And this is another problem for, to make a simultaneous prediction of all the demand, origin destination demand, and the demand from a zone in real time. I assume now what time? Now basically this is the brief outline of some research.
Thank you, Professor Yang. I think that's a very comprehensive overview of you have already done. I think that you have done a lot. Many years to achieve that. I have a quick question regarding to the. I'm very interested because the ride sharing is a part of the whole transportation system, and actually it's very important that we put that into the whole transportation system. In that case, you have to connect the data from other sources. Are you able to do that or not?
Oh yeah, I think I think very soon autonomous vehicle will be in market, and actually I have been thinking about the problem. With autonomous vehicle, of course, in the near future, I don't think we have complete just autonomous vehicles, right? We still have a mixed fleet of autonomous vehicle, of human driving vehicles, and in the ride sourcing market in particular, so we may have 3 types of service providers: autonomous vehicles, and full-time employee, full-time drivers, and part-time drivers. How can we come up an optimal mix of such labor supply? This is a question, all right? Question, interesting research question. But in this case, we should pay special attention to the variation of passenger demand. Okay, over time of the passenger demand variation, peak hour, off-peak hour, maybe during the peak hour, most of the provider will go to the market to provide the service. But during the off-peak hour, maybe just autonomous vehicle or full-time drivers provide the services. So we should have an optimal mix of the labor supply. So this is the question I just asked a new peer student to look at this problem. This is a very good point. All right, everybody talk about autonomous vehicles.
Okay, thank you.
Yeah. That's all.
Yeah, that's I think we have the next speakers. Could you unshare?
9 o'clock. Thank you for your attention. Okay, keep in touch.
We'll introduce the speaker.
Keep in touch. Okay.
Thank you. We'll talk to you later.
Yeah.
Dad, I need it right now.
I think you need to unshare your screen because I think.
Now I already told my share, you can share.
Yeah. I think the professor. No, I have a meeting. We will finish the 今天的 talk. Oh, sorry. No. I think let's move to the next speaker.
No, you're not allowed to leave it right now.
Could you share the screen, Professor Varakatham?
Yeah, I'm about to share my screen. Yeah.
You share screen, and I think our next keynote speaker is Professor Pradeep Varakatham. Is the associate professor in the School for Information Systems at the Singapore Management University. He also has a joint appointment as a visiting researcher at Google Research India. His research is at the intersection of the artificial intelligence, operation research, and machine learning with a specific focus on solving the multi-agent sequential planning and learning problems. Pradeep has published extensively in top-tier conferences and journals in artificial intelligence and machine learning. Apart from publishing his research, he has led the transportation project that has been successfully deployed and in use by multiple government agencies pertaining to transportation safety and security in Singapore. He's a senior member of IJCAI, gave the earlier the career Sport Night in Talk at the International Joint Conference on the Artificial Intelligence, IJCAI 2016, has received the Google Researcher Award for Project on AI for Social Good. His paper has won the Best Application, Best Demo, and finalist at IJCAI 19 and AAMAS 2018, and informs innovative applications in analytical world respectively. Welcome. It's your turn.
Thank you. Thanks for the nice introduction. Just wanted to clarify that the appointment with Google has ended. So that was a short-term appointment, not a long-term one. So I just want to clarify about that. Yeah, thank you for the nice introduction. So today I'll be talking about our work over the last many years. And it is focused primarily on how cities can adapt when there are events that happen. Some of these events are regular events, like the demand coming through for taxis every day. And then there are certain kinds of events which are not so frequent, and basically they are more of shocks and disturbances to the system. So how do you adapt to that? So our research has focused on addressing these kinds of different types of events. And this is joint work with my students who were working with me previously, Abhinav, Meghna, Sanket, and collaborators, Patrick Jailet at MIT, Arunesh, who is at SMU, and Professor Milind Tambe at Harvard. Okay, so the motivation for my research comes from different types of matching problems. For instance, in case of taxis, you're trying to match taxis with customers, single or multiple, which we refer to as pooling problem, as was discussed in the previous talk. And then we have bike sharing problems, where you have to have the bikes match to the locations where they should be placed so that they get rented very quickly, and several other logistics problems, even related to food delivery. And then there's another set of matching problems which are more in safety critical environments, like matching ambulances to the base stations where they should be situated, or for matching security personnel or security equipment to the right location so that they can interfere any kinds of crimes that can happen. In short, the specific problem of interest in most of these problems is to match supply to demand continuously, online or offline. So it's not just about, I will do one match and then I am done. That's not the case here. We want to match, and then while matching that, we want to consider what will happen in the next step. It's like what we see in the taxi problem, right? Every time we make a match, the problem doesn't end there. There's a new set of demand that is coming in, and so on. So there is a stream of demand coming through, and we have to make our allocations so that over time the revenue is maximized. So that's basically the core problem of interest. And as you can imagine, given the scale is it's at city scale, there are lots of major challenges. Firstly, the objective itself may be centralized. That is, there is one aggregation system like Uber or Didi or Grab, where there's one aggregator and they are trying to maximize their revenue. Or in case of Singapore taxi system, the way it works is that each individual driver is their own owner. So they are trying to maximize their own individual revenue. And then we have uncertainty because the demand is not known beforehand. As I mentioned earlier, there is also the problem of sequential decision making. You're not just trying to maximize revenue for this time step, but you're also thinking about what happens in the future. So how do you do this multi-step decision making? And then scale, complexity and scale. You are trying to solve a problem at city scale, not a few agents, right? So that's always a major challenge. So just to put it in context, what my group's research focus has been on is if you put a complexity on one side and scale on another side, there've been lots of models trying to solve problems at different aspects of this two-dimensional axis, right? So we have models for solving small scale and large scale problems when things are deterministic, cooperative, or competitive agents. Similarly, when there is uncertainty, focus has primarily been on small scale problems, primarily because the problems are much more harder. You're having to deal with uncertainty. So our focus has been in this area where it is large scale, uncertain, cooperative, or competitive. So essentially, we are saying that we want to solve the most complex problems. Most complex problems at the highest scale. Now, why is that possible, or why is that even feasible? How come others have not thought about it, and so forth? So the key idea here, why we are able to focus on this, is our emphasis on urban environments. And there are some really nice properties of urban environments. And as I mentioned, so we are interested in these sequential matching problems. So it's not just myopically we are dealing with that. Now, the key idea is that at a higher level, the key idea is that we exploit the structural and operational properties of the domains. So one of those is anonymity in matches. Each individual taxi driver or each individual customer doesn't have a specific identity of their own. It doesn't matter what taxi gets matched for the customer. As long as they get a taxi, they don't care. It can be taxi A or taxi B or taxi C. So that's the anonymity in matches. And then the reward function that is used by the taxis, for instance, is homogeneous. It's not like every taxi driver has their own separate reward function. There's a meter, which is the same for everyone across the island. So that is also homogeneous. And a few other such properties which exist primarily in urban environments. That's what we try to exploit, right? And on top of that, because these are urban problems, a lot of these have large data sets that are available either for free, or once you talk with the right agencies, you are able to get these large data sets which can be studied properly. So that's been our overall approach. That's why we are able to move to this area. We are moving to that area, but with the caveat that it is in the context of urban environments. That's why we are able to look at these problems and provide certain kinds of solutions. So the results, we have been able to, some of these we have deployed, and some of these are on real world data sets related to taxi fleets, emergency response, bike sharing, traffic patrols, and certain parts of it were also on a theme park that was that's been there in Singapore for a while. Apart from research papers, we have also deployed our tools that we have developed. These tools have been in use by government agencies, or they've been going through some rigorous on-field deployment. Here are some of the ones. I'll not go through each one individually, but just as a broad statement, it's not only about the publications, but we have also tried to put these on the ground and see how well they function. Specifically in the context of this workshop, we developed a guidance system for taxis to find the customers. And this guidance system was developed based on a data set from Singapore Land Transport Authority, which has access to 40,000 taxis across the island. And the data was streaming to us. We didn't have control of all the taxi drivers, but we had control of about 500 taxi drivers. and we were able to provide guidance to them on where they should go next after dropping off a customer, so that they can make most optimal use of their time. And yeah, so we were able to reduce the idle time of the taxi drivers by 27%. Okay, coming to the specific research problems, we have looked at quite a lot of models and methods for solving these sequential matching problems. Under a single agent case where there is just one objective and everyone is thinking of that one objective. We have looked at multi-stage stochastic optimization, and we have looked at MDP and COMDP based matching. But what I will focus on today will be on reinforcement learning, and specifically with the added operative that it has to deal with operational constraints. So that's the key change from traditional reinforcement learning. We are having to deal with operational constraints on the ground, whether it is related to allocation or what is considered a good match and what is not considered a good match. And we also have work in multi-agents, which I'm not going to talk about, but there as well, we have used optimization, stochastic optimization with computational game theory. We have used POMDP-based, decentralized POMDP-based matching. And then we also have multi-agent deep RL for large-scale games. Okay, so I'll primarily talk about two of our works, which are the most relevant for this workshop. The first of which is neural approximate dynamic programming. And this is relevant for the ride pooling problem, where each taxi is being assigned to not just one customer, but a group of customers. So you're pooling the customers and assigning them to taxis. And the key change from existing work is that we are thinking over time, right? So we want the matching to be not just myopic, but thinking into the future. And then I'll talk about resource constrained reinforcement learning. This is another one of the models which deals with a slightly different problem. And in terms of transportation, it's related to bike share, but it is also relevant to ambulance allocation. So I will talk about these two primarily. We do have other work with other works which focus on constraints in reinforcement learning. I'll just briefly allude to it, but I'll primarily focus on these two works. Okay, so I'm assuming all of you are well aware of this problem, but just so we are all on the same page, I'm going to just quickly go through the problem definition. So in real-time ride pooling, what we have is at each round, we observe the incoming demand. And once the demand is in place, we have to match demand with supply. So here in this case, there's a blue vehicle which is being matched to the blue customers, red vehicle is being matched to the red customers, and so forth. So yeah, and green one to the green customers. Okay, and this matching has to be done while considering the constraints. There can be pickup constraints, there can be drop-off constraints. The pickup constraints is how long it will take for the taxi to reach the customer, and yeah, it has to be within a certain time window for it to be considered as acceptable. And then similarly, there is drop-off time window, which would be how long it will take to get to the destination. So that's the two main steps. And then we are trying to do this matching so as to optimize certain kind of reward. This reward could be the overall revenue that is earned or the number of requests served. And once this matching is done, we have to update the available resources for the next matching step, and so on. So that keeps going on. So in terms of putting it simply, we are trying to maximize not just the reward for one time step, but the total reward over T time step. So this is more like we can treat it as a single agent RL problem, because there is one aggregator who's trying to maximize something for itself. So why is this a challenging problem? Why is this real-time ride pooling a challenging problem? And I was unable to attend Alonso Moro's talk today morning, but I'm pretty sure this was mentioned because our work here is also improves on the work that Alonso Moro et al. Had in 2017. So why, I'll just rephrase the challenge. So why is it challenging? Why does when we introduce multiple capacity vehicles, why does it become a challenging problem? First of all, when you just have single capacity vehicles, as in each vehicle serves one request, the overall problem is primarily at a single stage is a bipartite matching problem. So each customer has to be assigned to one vehicle at the most. That's all. However, when it comes to ride pooling, it's no longer a bipartite matching problem. Instead, it is matching on a tripartite graph. There are 3 parties involved. These 3 parties are basically the customers, and then there is a combination of customer requests. And then there is taxis. So we want to match taxis to combinations of customers, and at any point in time, each taxi can only be assigned to one customer combination, and each customer can only be assigned to one active combination. So because of this, these two-way constraints, it can't be represented as a bipartite matching problem. And the other reason why it is, the 2 other reasons why it is challenging is that here we are not only looking at single step for decision making, we are also trying to look into the future on how we can consider what will happen later and use that to make good decision choices now. And the other thing is the online decision making, so you don't have forever to take these matching decisions. Typically, it is the limit that we imposed on ourselves, even given that we were working on academic machines, was that we will only have a minute at most, or even less. Yeah. So most of the existing work is has focused on myopic setting. That is, we want to maximize a number of requests served in that time step. So even the myopic problem is quite difficult, and trying to get good matchings and trying to focus on maximizing the overall objective is not easy, and it requires some very fundamental contributions. And our approach builds on top of those contributions and moves to the multi-stage or non-myopic case. And we are primarily in this space, which is where we are focusing on non-myopic, and we can consider requests in a batch, not just one by one. The requests can come in a batch. So we have, I'm primarily going to talk about this neural approximate dynamic programming work, but we have another work called SAC Benders, which is based on multi-stage stochastic optimization. Okay, so that's the key difference. We are focusing on non-myopic, and that's where non-myopic and high capacity vehicles, not just 1 or 2 capacity. Yeah. Okay, the key, I'll just outline the high level contributions we have made in this space, and I'll primarily talk about the RL work. The first contribution that we have is neural approximate dynamic programming. It is based off of approximate dynamic programming. And the idea is that we are matching vehicles to combinations of requests, also referred to as trips. And each request can be part of maximum 1 trip once it is assigned. And then we have a zone path-based stochastic optimization. Here we match vehicles to paths. Paths they should be taking so that, and each path is assigned to multiple requests. So this is a way for us to do the similar kind of matching. It's just that now a path can be assigned to multiple requests. This way of doing things enables us to not worry about combinatorial generation of there is no need for us to generate combinations of requests this way. We can find out paths which are the most active, and you assign vehicles to those paths. And yeah, it was shown to perform better than, even in the myopic case, this was shown to be better than the existing work by Alonso Moro et al. And then finally, the other piece of work which was a very fundamental contribution was when we have last mile transportation, where taxis are being used to move people from train stations or metro stations back to their houses nearby. Then we were able to show that using multi-capacity vehicles, then we were able to provide theoretical bounds on the competitive ratio. We were able to get a competitive ratio of 0.317. It's not great, but we were able to show that these are primarily first of its kind. People haven't been able to provide competitive ratio bounds for ride pooling problems. So that was a useful contribution of it. But anyway, I'll go back to the neural approximate dynamic programming work. So this is how it works. So there's an underlying MDP. The underlying MDP for the RL problem we're talking about. So the underlying MDP has a state which includes the current trajectory of all vehicles, where the trajectory corresponds to the ordered list of locations they have to visit later. So just to avoid having anything specific to a vehicle, we only store the ordered list of locations to visit for each of the vehicles that is present in the current, that is available in the current state. Then the action is the assignment of request group to vehicles, that is one combination of requests to one taxi, right? So you have to match that. And the transitions and rewards are not known in advance because we don't know the demand coming in. So we don't know that. And that's why we are proposing to use reinforcement learning approaches, wherein the simulator can be based on the past data. So the challenges here are that the number of joint states and actions is extremely large. That if we apply basic DQN, the neural network-based models, they just don't train at all, even after a long period of time. So that's where we started looking at other options. And the second issue is one on demand uncertainty. And then the third one, which we had to ignore when we applied DQN, was the constraints on action. So if you want to have matching constraint, which is that each taxi can only be assigned to one combination of requests, and there are pickup and drop off constraints and so forth. So those cannot be imposed if you're just using a basic deep reinforcement learning model. So that's one of the reasons why we have this new approach. And then the other issue is that we have to think into the future. So how do we deal with the non-myopic decision making? Okay, so before I move on, just to give a quick insight on how things work without our contributions. Normal way of designing an algorithm here is that you get the current set of requests that require transport, and then we generate and we also look at the available set of vehicles. So we generate all feasible trips. That is the thing in the middle. We generate all possible trips that would need to be matched. And then there is an ILP, which gets solved, wherein there is a exact match that is being done. So in this case, the green vehicle is being matched to request B, and red vehicle is being matched to request A. Right, and after that, you simulate the motion. As in the taxi moves to the next request, and so forth. And this loop keeps repeating. Now, with our approach, what we are essentially saying is that we have an underlying neural network, which, given a vehicle's current status, that would be the location where it is at, and the list of locations which it has to visit, and the current assignment, this neural network, the deep Q network, will give the value of making such an assignment. So we can retrieve all the vehicle request assignment combination values from the DQN, and we use that in the MILP. So we are no longer just trying to maximize the myopic reward. We are trying to maximize the overall value into the future. So when you're solving ILP, you are also looking at the future. So that's where the future part comes in. And then the updating of the score function. So how we improve this DQN is every time once an assignment is made, we look at what assignment was made, and for those assignment values, meaning for that action value, for that state, we assign the reward that was obtained. So this way, the DQN learns what exactly is happening with respect to the match. So it is understanding a little bit of the underlying constraints MILP is taking, even though it's not explicitly involved within the neural network. Based on the outcomes it is seeing, it's trying to learn what the ILP is doing, and it is assigning values by considering how much revenue is being earned into the future. So that's the key distinction. So that's the overall approach that we have. One of the big insights was that we build on top of approximate dynamic programming. And why are we able to do that is because transition probabilities are exogenous. That is, when you take an action, it does not have an impact on the ground. When we take an action, as in when the taxis take an action, which is to move around, that doesn't have any impact on the demand. Demand is going to come the way it is going to come. So it is completely independent of the actions being taken, the assignments being done. It's completely independent of it. So therefore, while in a normal MDP, we have this kind of state action trajectories, S0, A0, S1, and so on in an MDP. Whereas in an ADP, instead what we have is there is a S0, you take an action, which is your matching action, and then you deterministically transition to a pre-decision state or a post-decision state called S0A. So this transition, the first part is actually deterministic. And that's when the demand arrives. So the demand is what is uncertain. And then because of the demand, you move to a new state, S1. So you're dividing the transition into two parts. And this is what helps us in doing the value updates in a more scalable manner, as I will show in a little bit. Now, so in a normal ADP, in an ADP, the value update will then become like this. So V of ST is max over all the feasible actions, the objective, plus the future value. So this is essentially what we are solving in our ILP. The only issue here is that the value function is over the joint state. So that's not yet scalable, for which I will talk about in the next slide. But essentially, the ILP becomes one part of the value function update. And the second part of the value function update is based on how the demand come in, how the demand samples are coming in, how the requests are coming in. And you just have to take a expectation over all those demand samples. So this is where the neural network is employed to learn the value function. However, as I mentioned, because the value function is over the joint state, it can be quite daunting. The number of combinations is quite a lot. So one of the assumption or one of the approximation we did was that the value function will be the sum of the values of the individual states. And we try to then learn what these individual values are. Once you make this assumption, the value function does break down nicely. We do capture that the value function, the individual value function, is dependent on some features of the states of the neighboring agents. So we do capture a little bit of that in a very approximate way. So there is some aspect of the neighboring agents that is present in the individual value function. So this way, we are still capturing some part of the neighbors, not completely ignoring them, because that does have an impact on whether a request gets assigned to the current agent or not. And we had to do quite a few other small things to make sure that this entire thing works. The first of which is to stabilize the neural value function estimation using insights from DQN. And then for each location, when we pass inputs into the neural network, we use a low dimensional embedding for each location instead of like a one-hot representation. So that way, dependencies across locations are captured, if there are any. If we use one-hot representation, those cannot be captured. So this is just to indicate the kind of ILP that we solve after everything is in place. So as you can see, this first part is the immediate reward. This is the future part. And for the future part, we have VI. So we get an individual value function for the state that you have transitioned to, right? TIA is essentially the deterministic transition I was talking about, based on the action taken and based on the action taken and the current state. Yeah. So, and these constraints are essentially trying to say every taxi is assigned to at most one request. Yeah, at most one request, and each request is assigned to at most one taxi. So we did experiments on multiple data sets, but I'm going to primarily talk about the New York data set because that's the one that is freely available. And we also have results on another data set from another Asian city. This is a much bigger data set with 20,000 nodes, nodes being the intersection points of the entire road network, and edges are the connections between those nodes. And we get about 300 to 400 requests. And the number of taxis we varied because that's something that we can control to see how well performance improves over time. And I'm going to talk about both our approaches, the other one being the Zach Vendor's approach. This is based on stochastic optimization. What I will show is the service rate, which is a percentage of total requests served over 15 of the weekdays. As you can see, our non-myopic approaches, which is the new ADP, this one right here, and Zach Vendor's, both are non-myopic approaches. They were able to improve, especially with the new ADP approach, we were able to first up gain an improvement of 14.7%, which is a pretty significant jump. The Zach Vendor's was even better. This was developed later, but since the focus here is on RL, I'm going to mainly focus here on the new ADP approach. And here are some of the settings we did. Pickup time window was 5 minutes, drop-off time window was 10 minutes over whatever is the usual time it takes. Assignments can be computed in real time, in the sense we put a threshold of 60 seconds because we were working on academic machines which are not very powerful. If we have powerful machines with better CPUs, because we are primarily doing inference online, we're just taking the model. If that can be, if the MIP can be solved even faster, then that can be improved even further. And this was on another data set. Even here, we were able to obtain an improvement of about 6% over a myopic approach with our approaches. Okay, so that was the first part of the work. I'll move on to the second one. Which is on resource constrained reinforcement learning. In the first part, I talked about the matching constraints being evaluated outside the neural network, right? So how to do these matching and then learn from whatever the matching system is providing. It was outside the neural network, so it was not really differentiable and so on. So there are some issues with that. So in this work, what we are doing is we are looking at a slightly different set of problems, and that kind of approach worked really well. It improved the performance quite a bit. So it worked in the taxi case. Here we look at a second set of problems, which are based on online ambulance allocation and online bike sharing, which is to say, how do you move your resources, whether they be ambulances or bikes? How do we move them around online during the day based on how the demand is and so forth? So for this, we built a simulator, which were simulators which were based on real data. Mostly available online based on those data. So for the bike sharing, we had a separate collaboration with the company, but for ambulance allocation, we had data from online that we used to build this simulator. Essentially, we have, I'll talk about the ambulance allocation problem because that's more easier to explain. Bike sharing has a few complexities which are maybe not very easy to get into. So I will talk about for ambulance allocation. So where we have to allocate ambulances to the right set of base stations so that we maximize the incidents served within a certain amount of minutes during the day. It's like every request has to be attended to within 15 minutes of the request being raised, or 20 minutes within the request being raised. Whatever that is, that KPI can be decided by the agency. And what we observe is we observe the incident and traffic data. So the incident data would correspond to how the request demand is coming through the entire city, and also how the traffic is on the different freeways and so on. So you are getting a lot of this information. And the main reason why we have to do online allocation is that there can be traffic jams, which can lead to ambulances not being able to meet their KPI in certain areas of town, or there is big accidents or terrorist incidents and so on, which can lead to an increased need for ambulance resources in certain areas. So that's why we are talking about online allocation of ambulances. So the action is basically to allocate or reallocate ambulances to base stations when required. And the main constraints are, once again, operational constraints. The first thing is that the total ambulances that you have are fixed. The second thing is that the number of ambulances that you can position in a base station is limited. So there are capacity constraints. And then there are also more specific operational constraints that certain regions of Singapore can have a max, should not have, should at least have a minimum of so many ambulances at any point in time. So those kinds of zone level constraints are also there. So to address these problems, the main challenge when applying reinforcement learning in these cases is that because it's a city scale problem, once again, the issue becomes that the discrete action spaces that we have along with constraints cannot be handled by existing work. Here are a few of the ones that are the most relevant. First one is by these folks at I believe at Dulak Arnold et al. I forget which location it is they're from, but essentially they were dealing with large discrete action spaces, and while that is good, they are unable to handle constraints. The second important work was by Amos et al. On introducing constraint optimization or optimization problems into neural networks. And while this is again really good, it only works with very small scale problems because it's kind of like an optimal way of doing things. And in this work, we build off of this to provide our best approach. So what is the underlying problem? We have state, which is the current allocation, the latest demand pattern, the latest traffic pattern, and the current time. And the actions that we have to provide is the desired allocation, which is how many ambulances should be positioned at which location. Right. So A1, A2, A1, AK until AN, right? So it's a vector of allocation, and we convert this into a continuous action space so that we can build more faster approaches. We divide the action, each individual number of ambulances by the total number of ambulances that is present. So it converts to a continuous action space. And the key difference compared to a normal RL problem are these resource constraints. These resource constraints are on the action space, where we have the total sum of actions to be bounded by a certain capacity, right? And then each individual number of base stations number of ambulances you can assign to a base station is bounded from below and above. So the minimum that you have to put and the maximum that you can put. And the last one is the hierarchical constraints. And these hierarchical constraints indicate like at the level of, so at the bottom level, at the leaf node, we have base station level constraints. Then you have at the level of districts, maybe cities, then at the level of states, precincts, and so on. So you can have constraints at different levels of the hierarchy. And you have these bounds over all the base stations that are within a hierarchy. So there's a constraint over the region hierarchy. So the approach we are going to use is because we have converted the action space to a continuous action space, we employ this deep deterministic policy gradient method. And the way it works, before I go into DDPG, let me give a quick background of DQN, where you have a neural network, which given a state space, will calculate the Q value for all the different actions using traditional TD learning. So it gets the values for each of the actions and then picks the one which has the highest Q value. So the policy computation is greedy or epsilon greedy action selection. Now in DQN, we have continuous action space. So that kind of maximizing over all the actions is not easy to do. So for that, the way it works is that we have two parts. The first part is the critique network. The critique network takes as input state and action, and it gives the Q value corresponding to that. But this action, who gives it? There is an actor network. So there's another neural network which takes the state, takes state as input and gives action as output. And this actor network gets optimized based on the loss that the critique network faces, right? So there is no explicit loss function here for the actor. So this gets back propagated. And once that is done, the actor learns to output greedy action using the gradient descent to maximize QSA. So this would be essentially your gradient. The first part is gradient of the critique network, and the second part is the gradient of the actor network. So that's a very quick intro of DDPG. And we tried multiple methods to solve this problem where we have to deal with these constraints. The first of which is the obvious choice, is to add some penalty whenever the constraints are violated, right? So you train the actor to give feasible action by adding a violation cost term to actor's update equation. So if y is being, there is a sigmoid function so that it generates this y function, and we have this penalty term. The penalty term of y is basically, for sigmoid, you're putting everything in 0, 1. But basically this penalty term tries to look at how much the constraints are violated. This is the capacity constraint, the first one. The second one is the max, the individual zone constraints, right? Or the bound constraints and so forth. So this is your penalty term, which gets added to the, or which gets subtracted from the overall gradient here, minus lambda, that's hyperparameter, into the penalty term. The issue with this is that there's no guarantee that the output y is always feasible, primarily because penalty doesn't guarantee that the action is feasible. But when you are executing, you still need a feasible action. So what we do is we have another quadratic programming, another quadratic program, which finds the nearest projection to the y that is feasible, that satisfies all the constraints, right? And that is outputted. That is the output that we get for the action space. However, the challenge still remains that we are evaluating Q for something that may not be feasible, and that it works reasonably well, but as you will see, we can do better. And the second approach that we tried was the constraint softmax approach. So for ensuring the overall capacity is met, we can use a softmax approach. But here, since we have other bound constraints, how do we ensure those constraints are met? And for that, we thought we can introduce what we call the CS layer as part of the actor network. So there's an explicit neural network, explicit layer, which is trying to enforce the constraints. And how does this work? If you have a normal softmax, then you have something like this, right? So ZK is e power xk by summation over I, all the other e power xi's, right? Now, when we have constraint softmax, we were able to come up with an expression which was quite simple, very similar to softmax, but it ensured that the different constraints are satisfied. So we were able to improvise softmax expression to enforce local max constraints. And that expression was very simple. So this ZK depends on the y's, which is e power xk, and then the lower bound, upper bound. And its expression was yk plus epsilon k by yi plus epsilon I. So just one additional term. This was really a surprise for us, because we didn't think that just by adding a term we can calculate this, we can enforce the constraints, but it does work mostly. This epsilon k has to take on a specific form, which is based on the lower and upper bounds, right? So that's the kind of structure we have. And there's a proof in the paper, which or multiple proofs that we had to go through to ensure we can get this value. And it was obtained based on enforcing monotonicity properties on this. That is, whenever the input to the CS layer increases, that is, the value coming into CS layer increases, the Z corresponding to that also should go up, right? So the probability of picking that component having higher allocation should also go up. So that kind of monotonicity properties were used to come up with this epsilon k. And you can use that, you can extend it. However, there was one problem, which is that this epsilon k had to be greater than 0. If it is less than 0, and it is possible to create pathological scenarios where this epsilon k is not 0. So it only works in specific cases where epsilon k is greater than 0. So that was a limitation. So this works, it's very easy, very scalable, but it has this constraint that it doesn't work everywhere. So therefore, we moved on to another, the last of our contributions, where we build on top of approximate optimized, we build on top of optimization layer work by Amos et al., where they have an optimization problem sitting within the neural network. However, and the main idea there was that you can differentiate. So there is a forward pass where you calculate what the output from the quadratic program is, but you can also pass the gradients back through the optimization problem using the implicit function theorem. And that was the big contribution. However, there is one big challenge, which is that you have to solve QP for a forward pass, assuming that is fast, but the inversion, which is when you're passing the gradients back through the optimization problem, that's an n cube operation. And in our case, when we are solving a city scale problem, this n can be quite big and it becomes extremely slow. Anything beyond a few variables, it cannot handle. So that's where we employed an approximate opt layer, or we came up with an approximate opt layer. The key insight is that our model constraints are very specific. We have upper and lower bound constraints, and then the summation or the capacity constraint. So because it is, because our constraints are a lot more specific, so that's why we thought we will build something specific in how the forward and the backward passes work. Firstly, what we can do is that the first insight is that we don't have to find the most optimal solution. That is, we don't have to find the Z which is absolutely the closest to Y. Any differentiable feasible projection suffices. And this is the key insight. Once you convert an optimization problem to a satisficing solution or satisficing problem, then things are a lot easier. We can provide like a semi-closed form, semi-iterative projection approach, where you take some constraints, solve it very quickly using QP, and then we patch up the solution. Whatever solution we get, it will not satisfy all the other constraints, but we can incrementally modify it and guarantee that you will get a feasible solution in the end. And that was our main contribution. And the good thing with this is that this feasible mapping is straightforward to differentiate through, doesn't require that n-cube complexity. In fact, it is less than order n, I would say, and then or less than order n. And the mapping is approximately nearest feasible. So it's not exact, but it is approximate. And yeah, so since I'm running out of time, I'll quickly go through this. The idea is that first we generate, as you can see with the blue line here, the way it works is that first it doesn't satisfy all the bounds, but over time you clamp and redistribute. That is, you upper bound, lower bound, you keep improving the bounds, and then finally it converges. And it only takes a few iterations to get to that final solution. Even the derivatives that you retrieve are much simpler. Okay, and we did experiments with two domains. First is the ambulance domain and then the bike sharing domain. Within ambulance, we had two types of variations. The first one is the Poisson demand pattern, meaning very predictable. We took average data from Singapore emergency response that is available online, and then tried to generate demands based on that. And then the second one, which is a more interesting one, where we created random surges with different amplitude and different duration of the surge, which is essentially indicative of bad things happening. So, and we compared against greedy static baseline, which is usually the kind of approach that you take when trying to allocate ambulances. And for bike sharing, the data itself, this is real data, so there's no non-Poisson thing. And we compared against optimization-based repositioning approach. And what we were able to see was that when the demand is Poisson, meaning things are pretty regular, then you don't really need any of our allocation approaches, anything related to DDPG. They performed on par with the baseline. In fact, baseline was maybe slightly even better than our approaches. So if the demand is Poisson, there are not many surges at all, then there's no point applying this. But when there are surges, what we saw was that especially our approximate opt layer was providing a significant impact, almost 20 to 30% improvement over the baseline. And 15% improvement over the greedy baseline. And in case of bike sharing, all the approaches that we developed were able to improve. So in this case, in the left graph, higher is better. In the right graph, lower is better, because we are looking at lost demand. And in the bike sharing case, and what we saw was, compared to the baseline, we were able to get about 50% of improvement using our DDPG based approaches. Yeah, so RL basically shines when the demand pattern is more nuanced than Poisson, because if the demand is Poisson, then there is no memory required. You don't really need something which is thinking into the future. Those reactive policy is, I mean, when it is more nuanced and when the demand is not just coming according to some prefixed values, then you can have something more valuable by using a reactive policy. Okay. Yeah. So just to make sure I leave some time for questions, I'll stop here. Yeah, sure. Okay, there is a question from Tony. In the ADP method for ride pooling, is generating feasible trips done online or offline? Is it a computational bottleneck? Yeah, so it is still done online, Tony. So we actually use the approach by Alonso Mora et al. To generate those feasible trips. It's the same approach they used. And the way it works is that as long as the capacity is less than 4, we can generate, it's an exact generation of all the combinations. But if it is above 4, we use a dynamic programming trick that was recommended in that paper, which is we only take the combinations that are generated for smaller capacity and then just add requests on top of those combinations. So it's a pretty scalable approach. What about directly clip the action to meet the constraints? Jerry, I'm not sure what you mean by directly clip the action. Which action are you talking about? So the action in case of ride pooling would be you are assigning to a bunch of requests, right? One action corresponds to a combination of requests. So it's not that easy to just take a subset of that and ensure the constraint is met. It's not that straightforward. That was the main contribution from Alonso Mora et al. I think that was a very interesting contribution because they were able to do this in a scalable manner.
I think we have to move to the next talk. Okay. Thank you, Pradeep.
Yeah.
Very nice talk.
Yeah. Thank you. Thanks. Bye.
Okay. So now we move to the last keynote session of today's workshop. And we have Dr. Jesse Lee from IJCAI Academy of Engineering. Okay. Dr. Lee is a chief scientist at IJCAI Academy of Engineering, and her research has been focusing on innovating spatial temporal data mining techniques to address real-world problems in cities, environment, and society. She is now dedicated to work on city intelligence. She had obtained her PhD in computer science from UIUC and was a tenured associate professor at Penn State University. So without further ado, let's welcome Jesse.
Okay, thanks, Ben. Can you hear me? Is it
Yes.
good?
Yeah,
Okay,
perfect.
good. Okay. Thanks, everyone. Since I'm the last talk, I will try to make it a little bit short. So rather than talking technical details as the previous speaker, I think my talk will be quite straightforward, and it'll be more like, I think, an open discussion instead of more of a technique sharing. So I would like to talk about the lessons I learned from doing reinforcement learning for traffic signal control. So my motivation actually started working on traffic signal control is actually when I look at the real world cases, the traffic is not moving. Obviously, there's traffic congestion, but even at midnight, actually the traffic are not moving very fast. This is the real data from Hangzhou when I saw it in 2018. And you can see this is almost midnight on a normal Tuesday. But the vehicle speed, on the major roads, only 28 km/h, which is quite slow. To understand this is actually the problem of the traffic signal. This is just a case. As you can see, this is almost midnight, and there's a very long queue waiting for take the left turn, even though there's no really vehicles moving on the other directions. As you can see, very few vehicles are moving on the other directions. This long queue is still waiting. So this video is playing at the 2 times of the actual speed. You can see this intersection is not fully utilized because of the not very well adjusted traffic signals. So after very long waiting, you can see this left turn car finally start taking the left turn. And they waited almost for 2 minutes, even though there are not too many vehicles in the other directions. So this really just inspired me to solve the problems in the real world. Obviously, the traffic signals are not very good today. And while looking into this problem, so that was the time I was taking sabbatical leave in Hangzhou. And when I look at this problem, I realized at least most of the traffic signal control system in China, they're still using the SCADs or similar system that was originated from 1980s, almost 40 years ago. And the idea of this traffic signal control system are mostly based on manually pre-designed traffic signal plans. it really surprised me. After 40 years development, we are still using this actually very like a very original traffic signal control system. And it's especially difficult for the cities in China because the traffic actually changes so much because of the construction in the cities today. So the pre-designed traffic signal plans can be easily outdated and doesn't fit today's traffic. But really no one is adjusting those traffic signal plans every day. So that's caused what we just saw the previous case, where there's a long queue of cars taking left, maybe because of a new residential building built nearby, but the traffic signals are not adjusted accordingly. So that really motivates me because we have so much data today. We have thousands of traffic cameras today capturing the traffic situations. Is there a better way that we can help improve the traffic signal? That motivates me to study this problem. And when I look a little bit further into the traditional transportation research, the traditional way they're doing this is solving optimization problem by using some kind of assumption. For example, they may assume the cars moving at a uniform speed, but obviously those assumptions do not hold in the real world. So that's why the traditional method doesn't really apply in the real world. And in 2017 or 18, of course, because of the AlphaGo, that inspired me to use reinforcement learning to solve this traffic signal problem. And the idea, of course, is very straightforward. Is it possible we take some action in the real world and we learn from the feedback how to better adjust the traffic signal instead of making the assumption and solve this optimization problem? And to apply reinforcement learning on traffic signal control, and since people in this workshop are mostly expert in reinforcement learning, so I won't go into detail, but the idea is quite straightforward. As you can see, we can treat the traffic situation as the state, right? And then the action will basically say whether we turn it into red or green. And say if we turn it into green and the traffic moves faster, and the reward goes up, then maybe next time in the similar state, we'll use the similar action. And if we keep it as red and then traffic gets stuck, and then the reward will go down, next time we'll not use this action. So simply we use this try and error idea. So we, at first, in our very first work in 2018, published in KDD, we used a very simple DQN to do this. And the idea is to learn the state at this intersection and the action. So learning the Q function of the state action pair and to see whether this is a good action or not. So we can do the similar, we can do the high reward action next round. Okay, so during the past almost 3 years, we actually published the serious work on this direction using reinforcement learning for traffic signal control. And we realized there are 3 biggest challenges than this topic. The first challenge is how to design objective function. The second is how to learn faster. And the third challenge, which I think is the most challenging topic, is how to address the reality gap. So in each of these, we publish several works. So I don't want to go into details of the first 2. The basic idea of the first challenge in terms of how to address, how to design a better objective function, the lessons I learned is actually you should look into the literature in transportation. There are actually many good measures already being proposed. Instead of you propose your own measure, it's better to use their actually well-studied measures. One thing we learned is actually the KDD work we published in 2019 using the max pressure, which was proposed by transportation people. It turns out to be a very effective objective function, the reward function. So the second challenge, learning, there are many tricks that you can use. We also publish a line of works. For example, you can better define the state, define the features of the state. You can learn from the demonstration instead of always try from scratch. So there are many different ways to make the learning faster and make it converge faster. However, actually, you can see my publication records in most recent years. We try to focus on the last one. So it's how to address reality gap, because we realize all the previous work, we actually using the simulator, but the simulator, obviously, there's a gap. And how to bridge this gap is what we really focus on in the past, most recently. So I would like to share a little bit what we did in this direction. So as I just mentioned, so the models we all published so far is actually in the simulation environment, right? And this is usually the simulation, traffic simulation environment. But the real environment will look like this. As you can see, it's very complicated. So there will be people crossing the roads. There will be different kinds of vehicles. There will be even some motorcycles. So it's actually very complicated environment instead of the very ideal environment in the simulation. So that means the best model you learned in the simulation environment does not apply in the real environment. And we have to acknowledge there's always a reality gap where it's between the simulation environment and the real environment. So starting from 2019, actually, I started focusing on this problem, how to, I call it learning to simulate. The idea is how can we learn from the real world data to learn a simulator so we can bridge the gap. So the idea is actually from the state at the timestamp t, from the simulator, if the next state transition will be say state t+1, and in the real world, the next state will be s t+1. So we want to bridge the gap between the s cap and s, right? So that was the basic idea. We want to make the state transition the same as the real world transition. So we've done several work. One work we've done, which I think is quite interesting. We published in both IJCAI and PKDD. In PKDD, we won the best paper award. So the idea is actually using the inverse reinforcement learning. We try to learn from the real trajectory, try to simulate the real trajectory. So this is the example. Suppose the gray one is the real trajectory, as you can see. And then suppose we only observe we only have sparse observation because we assume we can only observe the cars where there's a traffic camera. So we only observe at certain locations of this vehicle's movement. So we want to simulate the actual movement using the traffic model, the car movement model. So the other lines are using other methods like behavior cloning or simple Gale, those kind of methods. The idea we propose here is combine the inverse reinforcement learning with the missing data interpolation. So the blue one is what we proposed. So we can actually simulate the actual trajectory much better. So the idea of the learning to simulate, we try to better learn how people drive, the driving behavior, how people do the routing, and also what is the actual origin destination from what we observe, the sparse observations on the roads. So that was the idea of those kind of work. Mostly we use different kind of methods, and we find that reverse reinforcement learning was quite useful in doing this, learning the driving behavior. So I won't go into detail of those works. We have several works published recently. You can refer to the papers. But what I really learned is actually after several published works, I realized no matter how hard I tried, there's always a gap. So I can make the simulator more real, but no matter what, I can't make it exactly the same. So actually that really makes me frustrated. Even though this direction, when we submit papers, people always like this topic of learning to simulate, but to make it really apply in the real world, there's always a gap. So I started looking more into this direction, how to really bridge this reality gap. I look into some of the work in the robotics field because people in robotics use a lot of reinforcement learning. And I find this workshop quite interesting. In case maybe some of you already saw it, it was a debate between whether we should invest into sim to real, or whether we should not invest in sim to real. Basically, whether we should build a simulator or not. So actually, it was very interesting debate. I suggest you, if you haven't looked into it, you can watch the YouTube online. So actually, before a debate, more people, about 88% of the people disagree investing into sim to real is waste of time and money. That means 88% of people actually think it worth building a simulator, whereas only 12% people think it doesn't worth building the simulator. But after this debate, where I think they have 30 minutes or 1 hour debate, actually 10% people move from disagree to agree. So that means that actually more people agree that building the simulator is a waste of time and money, which is actually what I was doing in the previous work I just mentioned. So I think that was an inspiring debate. And also I talked with Jieping, which Tony must be quite familiar with. He was at DD. I invited him to give a talk at my workshop at KDD last year. And I think what Jieping mentioned was quite inspiring. So Jieping told me that the simulator, you don't have to make, the state transition exactly the same, but you can make the simulator as a reference for A/B testing. For example, there are 2 actions. You don't know which one is better, but you can try it in the simulator, and the simulator tell you action A is better than action B. And in the real world, the action A is also better than action B. So that means the simulator can still tell you, relatively which is a better action. So this is a relatively more doable job compared with you want to do the state transition prediction, which is I think is quite inspiring. Another thing I found quite inspiring is I further look into some control work. Maybe some of you in the audience already know. I watched Professor Ben Resch some talk, and he was saying actually in the control, this simulation model is already part of the control loop. So they were learning the model because essentially what I mean simulation model is the state transition model. So this model is being learned at the same time they're doing the control. So actually this is not something new in the control field, where they're combining taking the final actions with the model learning. That's also something quite inspiring to me. So as I said at the very beginning of the talk, this might be more of an open discussion instead of discussing the details of my own work. So I personally find those discussions are very inspiring. I don't say I have a solution now, but I see different kind of approaches. People are talking about whether building a simulator or not. So I do want to also mention a very interesting competition we were hosting on this topic at KDD Cup, which was just finished last month. It started in April and took 3 months to finish. And the KDD Cup, we hosted the idea. The task is actually traffic signal control, but we use a different kind of, a slightly different kind of format. We ask how many vehicles can you serve at the most with the city scale road network. So basically, we ask the question, how many trips can you finish by keeping the delay factor less than 1.5? So as long as one vehicle is above the threshold of delay more than 1.5, this round will actually be ended because it actually above the threshold. So as long as you can keep the delay factor below 1.5, you can keep running, and we can see who has the best method by tuning the traffic signal can serve the most traffics. So that was the idea. We had more than 1,000 teams from almost 300 institutions that made more than 3,000 submissions to join this challenge. And we provided a simulation environment, which is here. As you can see, it's a city scale traffic simulation environment. We started building our own public traffic simulator I think from 2 years ago, and we'll talk a little bit more about this later. And we also, in this competition, we also provide the cloud computing cluster with almost 5,000 cores and a lot of memory for people to actually train their model. So this is also the first time, as far as I know, in KDD Cup, we are providing the computing resource for people to compete. So the participants are changing the traffic signal plans, as I mentioned, as long as they keep the delay factor less than 1.5, how many vehicles can they serve at the most? So this is the simulator we built, and it is the first public simulator that can simulate the city scale microscopic traffic. I actually saw on this workshop, there is also a paper talking about the traffic simulator. I didn't listen to the presentation. I'm just curious, maybe there's some overlap, but we actually published a simulator 2 years back, and we have been refining it after that. And this is, as far as I know, the fattest public simulator that can do the microscopic traffic simulation. So we provide this, and we provide a computing resource. And the final results, we have 3 different phases. Only 20 teams enter the last phase. And I show a screenshot of the top 10 teams. And you can see, even though this is a problem that seems quite straightforward, but the top team, the first one, can serve 15% more vehicles than the 10th, not to mention the later on, the other teams. So actually there is still a quite big difference in those, in the teams who participated in the final phase. We find this quite interesting. And also, the more interesting thing I would like to share here is actually people using the top team actually didn't use any of the deep learning method. They simply used the parameter search. So basically they were trying different kind of ways to know what is the car following model, what's the driving behaviors that was set in our simulator. Because we also provide computing resources. So actually they extensively used our computing resource to do the parameter search, and they ranked the top in our competition. And in the top 10 teams, surprisingly, actually 6 of the teams doesn't use neural nets at all. Only 4 of them use the neural nets to fit this traffic model. The others are simply doing the parameter search. So as I said, we also provided computing resource, and the top team used 80% of CPU over a 3-week-long final period, which actually is using it very extensively. So that means like almost like every day he was using it 24 hours. So it's just something very interesting. As you can also see, Sumo, who is also a very popular traffic simulator. That is the team actually from the Sumo's team, the actual Sumo team from Germany. They also participated in our competition. They didn't really use our CPU. Let me check the method. They also used the parameter search. They ranked number 5 in our final results. So as I said, this might be more of an open discussion. I tend to make it short because I'm the last. People probably are tired. So I would like to share the last message, what I learned recently, even though this doesn't seem like a very organized talk. But what I really learned is, I think 3 years ago, 2018, when I started doing this work, I was more of a method-driven mindset. I was using, because of reinforcement learning was quite useful, was quite a hot topic at that time. So I was trying to use the reinforcement learning to address the traffic signal control problem. I was thinking, oh, this is a very nice, nice technique with a real world problem. So maybe I can do something really cool. But after 3 years of, research, and also talking with different people, doing more literature survey, I actually changed my mindset a little bit. I think it's more important to do a problem-driven, have a problem-driven mindset instead of using a certain technique to solve the problem. Maybe we should start with the actual problem and start finding the solution. So this is what I just mentioned. I actually spent quite a long time building the real simulator, but I realized there's always a gap. I hosted a challenge and I realized actually the top solution was using the parameter search instead of anything related to neural nets. So that really gives me a different perspective. I would like to end my talk with really the lessons I learned. I think the number one lesson is when you really look at the problems, no matter how real the simulator is, there is always a gap. It doesn't mean that you shouldn't build a simulator. I spent a lot of efforts building a simulator to make it faster, to make it more real. But you have to acknowledge there's always a gap. And lesson two, I think more importantly, if you try to address the real world problem, is more important. Don't just always focus on trying to bridge the gap. And it's more important to actually solve the problem. That is also why I think Tony knows that I was a professor at Penn State University. Actually, I recently resigned from the university. I joined Vinci Academy of Engineering because I feel now is the time. I really want to do something more practical, and I want to really solve the problem instead of always using certain technique to address the problem. So I think that will end my talk. I think it's a bit short, but since this is the last talk, I would like to take if there's any question.
Yeah.
Okay.
Yeah. May I ask a question? Hi.
Yeah, sure.
Hello, Jesse. This is my first time to listen to your presentation, but I find it very interesting. Okay, I'm Haiyang from civil engineer. Okay, working on transportation. Just one question about your KDD computation, the signal control simulation. Your title is how many vehicles can be solved. I suppose one vehicle means one trip, right? By vehicle completed, right? But that's that normally we when we measure the output, okay, of a traffic system, we do consider the number of trips and also the distance, because if you have too many short distance trips, of course you can complete more vehicles. You solve more vehicles, more trips. So why don't I consider the total vehicle kilometer as your output? How did they consider the trip length distribution?
Yeah, that's a very good question. That's a very good question. I think that's also a major we can consider. But one thing I would like to mention is actually every participant have the same OD trips to finish, same origin and destination, and they will appear at the same time. So if for longer trips, as you just mentioned, maybe you are raising this, like maybe some participants make the shorter trips finish faster, right? And with the longer trip, as still on the way. That's why we have this delay factor. So they won't make this long trip, even it's a long trip, as long as the current waiting time, based on the current waiting time, and also based on expected, even if there's no red light at all, how long it will take to finish the whole trip. If that one exceeds the delay factor 1.5, they will still fail. So did I answer? Did you get what I'm saying? So even for the longer trip, we do consider, the rest of the unfinished trip, how long it will take to finish, to decide this delay factor. It's not only by, so far how long it traveled.
Okay, thank you.
Yeah, Jesse, I think there's a very nice discussion, and I generally agree with your the comments in the last slide. And actually, I just share my personal experience about simulating how to solve the real problems. I work in both in academia and the industry because this is really when you work in the academia is your scope is much smaller, and because you don't have enough resources, and for most of the, in particular for junior faculty, even for senior person, you may not have enough resource to do a lot of things. And therefore, the network questions you're trying to solve is limited by amount of resources you can do, and therefore, and also, academia, you have the pressure because you always need to publish papers for yourself at the beginning and for your students, and later, okay, and therefore you have to be always. Think about, in many cases, most of the faculty members in academia always basically I try to develop the tools or just using one tool to apply to everywhere they could, and but that's the could be people you can always get paper published because most of the other people do the same thing. I have a tools. I think it's just not hammers. I hammer here A B C D. To many different places, then you basically you have 10 different places, you get 10 papers at least. Okay, and it's very common, but I think that in generally science doesn't really move that way. Okay, because I think even for academia and the industry, when I work in the industry, I really realized how important you solve the real problems. And but I think when for people from academia, then they always think about the problems and whether I can write a paper on. But actually, if you work in companies, the problems you try to solve may not be really interesting for these people and use them like the manage basically in a specific business. I don't really care about the problem you solve because that I don't really gain anything by, or you get a little bit. And why should I invest resource on it? Because that's you have to change the mindset when you work in the basically industry, and that's a totally different aspect. But also because when you're in the industry, why do they care? In many cases, you will see that, and they don't really. The most business people, they don't really have very strong training in methodology at all. But they have very strong training in business. They know what kind of problems are very important. You have to solve them in order to start the business. And in many cases, they don't really start with basically solve technical problems. They just basically they set up the infrastructures, and then you're basically they're using a rule-based method to basically solve like a 50 or 70 or even 60% of the problems. And because then they set up the whole infrastructure and make their business start to run. And after a while, when they have more data and more other things, then I think the technical could help. Okay, and then you collect more data, you realize more about the real business. Then you basically you have to set up feature engineering, all this stuff, and basically solve. You have specific real problems. You have to solve it one by one based on the importance to the business, and that's the totally different way of solving the problems in the business settings compared with university academia. I think the simulator. I have a dream to do a simulator. But actually, in real kinds of the business, we will always try to meet the need of all these business people. We need to solve the problem they really care, not the problem we care. And then that's the fair.
I think you raised a very interesting point. Actually, I didn't mention too much about what the institute I'm in right now is neither university or industry. And IJCAI Academy of Engineering is a nonprofit entity in China. So as you just mentioned, actually industry has its pros and cons as well. That's why I actually didn't join the industry. I didn't join the company because, there will be a lot of pressure of the business from the business side where you have to, use the simple method to solve their problem. But at the same time, I am looking for an intellectual challenge, right? So that's why I made a decision to join this nonprofit organization, so that on one side, I don't have to, publish because I want to publish. And the other hand, I don't have to, just simply provide a solution just because of the business, so that's why maybe I will fail. Okay, I think I'm doing, simply give a try to this nonprofit organization. But I think at least so far, I joined here in January. So far, I feel like every day I'm doing what I'm really interested in, without really the pressure to publish, or without the pressure to get money.
No, I think Jesse, I think I want to make another point is, even though we have to meet the need for the business people, but actually because we have some other experience. I think the simulator itself and is great, but I think you have to take a longer. I think it's a long-term goal when you do these things. You still can have, because in the business, actually, we have certain resources and to do it. Like I was at the DD, I think, like Tony and these teams, and we really use them for long-term kind of achievement. And we really do something, invest some resources doing like simulators. But actually, when we do this big project, it's not a small project. It's a very big project, but we just allocate the resources in each of these directions. Each direction, actually, business people really, the people from business units do care about each of these directions. But we tried to basically looking at it from global set, the high level, and try to link all the things together. But if you want to do something big, I think the simulator is eventual goal. It's not like a very small scale. You have to solve the problem from a global scale. But take the years to do it. It's a long-term goals. But I don't think it is. I'm not always doing by business the person when I collaborate with them and I provide a service with them. But I always allocate a small amount of resources to do something. I think that's eventually contributed for long-term rewards. That's why what I did, even in academia, I do the similar things. When I do something, I'm not just invest all my resources in one specific topic. I will aim some high, but it's taking a much longer investment for doing it. I don't think that's would be too. I think that that's a conflict of insight, but you have to control it by yourself.
Yeah, thanks, Hontu, for your suggestions. I think Tony was raising hand for a while.
Yeah, I don't think I get comments on
it. Hey, Jesse. Yeah, thanks for the very thought-provoking presentation. So I'm actually just wondering, let's take traffic signal control as an example. So what aspects of the simulation and real world gap that you think is most, I don't know, detrimental to the reinforcement learning based agents? So I mean, now we pretty much acknowledge that there's going to be a gap, so I'm just wondering, like, in traffic signals control specifically, what aspect of that gap is the most undesirable?
Actually, for that's a very good question. For the traffic signal control, I think the most desirable gap to be filled is the driving behavior at the intersection. So basically put this question. So if you give, say, 30 seconds of green light to this direction, how many cars can actually pass through? So that simple
Mhm.
question. So, you know, so first, maybe we don't even need to learn exactly how the vehicles are moving on the road, but simply answering the question for this intersection, if I give 30 seconds straight, 30 seconds left turn, how many cars can actually pass? And this may vary, you know, at different times. You know, during say peak times, maybe there are also pedestrians, right? So especially in China, there are many pedestrians crossing the road. So those times, even if you turn the, you know, the left turn on, the cars may not successfully pass because of the pedestrian are crossing the road at the same time. So I think that seems to me that's the, you know, most tricky question at this point. But to actually answer that, you need a little bit more, a very comprehensive, you know, data at that intersection. You know, you need the data, actually the cameras at different directions, so you can see the whole picture of that intersection. That's why it makes it a little bit hard, because right now the situation is the cameras are usually facing at a certain direction. So maybe I have the north-south direction, but I don't have the, you know, the east-west direction. So it's really hard to find the intersection to give you the full picture. And also, of course, the intersections vary because of different, you know, the length, the width of different intersection. That makes the problem quite difficult. Yeah.
So then as you said in the presentation, you know, there's always going to be a gap between simulation and real world. So does that mean maybe we should focus our effort on training a basically a robust agent that can at least be aware of the differences in the environment that the agent is in, and then basically instead of aiming for the optimality in the training environment, it just have to be able to adapt to, you know, all kinds of situation. And in the real world, you know, it's always hard to to learn those edge cases and put into the simulation. So does that mean maybe we should just focus on building something just more robust?
Yeah, I think that's one direction I'm seriously considering. That's why I was having this slide. I find, you know, the control people, actually the work they do are quite inspiring. Because, you know, the biggest thing in control is the robust control, right? So they actually do consider these uncertainties when they do the control. They never assume the simulation model is perfect. They never assume the state transition is exactly the same in the real world. So there's a lot of work has been done in the robust control, which I think we should learn, you know, a lot from them. But I don't really think they would directly address the problem. Mostly because I feel, at least as far as I know, the environment that they are facing are still relatively simple compared with the environment, what I was talking about, the traffic environment, which is quite open and complex, involves people, you know, involves a lot of people's movement. So it'll be much more uncertain compared with usually their environment they're dealing with, and mostly, you know, mechanical environment, right? So, you know, control, you say air conditioner, control elevator, those kind of thing, right? So the control we are dealing with are much more complex than the typical control problems they're facing. So I don't really have a clear answer. I think the robustness definitely is a very important part. And I found their work quite inspiring. But still, as I mentioned at the very beginning, this is more of an open discussion. I don't have a solution now, but maybe next year, you know, I can share more of a practical experience.
Yeah, looking forward to that.
Okay.
I think I have a technical question. Maybe it's about the challenge one you mentioned in your presentation. I think according to my own experience, I think it is very important. If you formulate this problem as an MVP, it is very important to define a very good reward function. And I think sometimes even a simpler reward function works better than a very complicated one. So can you give us some insight about how to choose a reward function? I mean, if we don't have any prior information about the problem we are faced with, how to define a good reward function?
Yeah, I have some complementary slides here. I didn't mention in detail. So basically, what I learned is exactly the same you mentioned. Sometimes the simple reward works better than the complex one.
Mm-hmm.
So in the scenario of traffic signal control, you can think about the idea. The final objective should be minimize the travel time of cars, right? So that should be the ultimate goal of traffic signal control. Of course, we didn't talk about pedestrian, but that's another topic. But the travel time is actually hard to quantify because it actually includes the time that we're waiting at traffic signal, and also include the time of the free moving. So that's why we break it down. People typically only consider traffic signal one. And we actually, in our very earlier work, in our first work on this topic, we propose to use the reward function as the queue length plus waiting time plus delay. So these three together. But we realize one problem is, as you see, we cannot simply add these three together. So it must be a weighted sum of these three factors. And we feel that the results is actually quite sensitive to how you weight them, how you weight different terms. So later on, this work actually now is published. At that time, it was still an archive paper. Later on, we simplify this to only queue length, but we can actually prove this one can equal to the first three. Using some transportation theory, we can actually prove under certain conditions, this one can equal to the all the three add together. Of course, not one-to-one equal, but with certain, sort of constant ratio. We actually, in this paper, we proved under certain traffic flow model, we can prove this. If you optimize queue length, you'll be equal to you optimize the travel time. So this simplified function, actually, you can see like when we use the complex reward, so later on this was published, if you use the complex reward, we actually doesn't perform as well as we use the simple reward. And this was measured by the travel time. So that's a lesson. To simplify this, I only have 2 slides, but to simplify this, my lessons learned is, first of all, simple reward is definitely better than the complex one, because the complex one involves a lot of parameter tuning of different factors. And the second lesson I learned is look into the literature. For example, the transportation people, they already actually prove. I collaborated with people from transportation while I was at Penn State. They actually point out, how to prove this. It's not I proved this. Actually, they point out how to prove this. So actually, you can learn a lot from the people in the field how to design this reward function.
Mm-hmm. Okay.
Yeah. Actually, I have one more question. The signal control policy and also control objective depends very much on the traffic condition or time of day. During the peak hour, we have traffic congestion. So we focus on the throughput of individual junction. We try to discharge vehicles as much as possible. But during the off-peak hours, such as the midnight traffic example you mentioned in Hangzhou City, we don't have really traffic, very much congestion on the road. So normally our objective is to coordinate signal control, such as the offset among different junctions. Okay, coordinate traffic signal control to reduce this stop. How did they consider the different traffic situation, different traffic control policy for different traffic situations?
Yeah, this is a very good question. Actually, at the midnight, as you just mentioned, usually actually the problem can be break down into individual intersections because, because the traffic is not that heavy. As long as you solve the individual problems, actually you solve the whole problem, right? So that's what I think. Actually the tricky time is during the peak hour because once the previous intersection get overflow, that will affect the next intersection, will further affect the next one. So Dr. Yan, you're from the transportation, so you must know, right? The MFD is phenomenon, right? So where the cars get congested, and then eventually everyone is moving slower, right? After this critical point, everyone is moving slower. So you should actually block the cars further away before they start getting congested, because once they get congested, everything is worse, and then it's hard to turn it back. So actually, when the traffic is heavy, the coordination becomes much more important. You could coordinate even several intersections further away. So that's something I think at that time, actually, we don't really have a solution, but the lucky thing is, and then we realized some of the, if you only coordinate the adjacent intersections, that already, that already reduce the traffic, and that already make the problem much easier. So if you simply coordinate the adjacent ones, as I just mentioned, using the max pressure, using the pressure as the reward function, instead of simply using the Q length. So actually that will help. The pressure is basically considering two adjacent intersections, right? Whether I can still push this further. So using the pressure actually can work better at the peak time compared with simply using the Q length as the reward function. But that is still only coordinating adjacent intersections. In the very extreme case where everyone is flooding into the center, I think that's the case. That's still, we need to coordinate even further. But that is one I don't really have a solution. I look into MFD and the related scenario. I realize people in transportation did study a lot of MFD diagram, but really a few of them really propose how to solve this problem.
Yeah, you talk about the MFD. Okay, I don't think it's really useful for your individual signal control, because MFD is an aggregate traffic model for area wide. You work in Hangzhou. You know Professor Wang Dinghai and Professor Zhang Li, right? They are my friend.
Yeah, I think I heard of their name. Yeah, but I never met with them. Yeah.
Okay, they work on signal control. Okay, yeah. Great. I hope we can cooperate. Okay.
Yeah, sure. Yeah, drop me an email if you're interested in collaborating, because I'm now just full-time in Hangzhou now.
Yeah, normally I visit Hangzhou, Zhejiang Daxue almost every year, but recently due to COVID-19, I already didn't go there for long time.
Yeah. So when
next time,
when the
you're also
pandemic is
welcome
over.
to
Sure.
visit Hong Kong. Okay, I'm now in IJCAI.
Sure. Okay.
Okay, I think we had a very interesting after talk discussion, and I think if no more question, it's the end of today's all the sessions. And okay, thank you, Jesse.
Thanks, everyone. Okay.
Yeah, very good session. I enjoyed it very much.
Thank you, everyone.
Yeah. Bye-bye.
Bye.
Thanks. Bye, everyone.